You might think of the study of organic chemistry as nothing but a list of molecules to memorize and long names that go on forever. Learning the difference between 1-bromo-3-chlorobenzene and triethylene glycol is not exactly riveting stuff. However, as abstract as it might seem, organic chemistry is a part of science that has enormous implications and applications in everyday life. Organic chemistry is the study of substances found in living organisms, or, in other words, primarily the study of carbon compounds. That definition isn't perfect because there are molecules, like carbon dioxide, which are found outside of living things so often that they're not considered to be organic. The truth is a lot more complex than we used to think, though this definition remains a good place to start. If we understand organic molecules and how they work, then we can better understand how humans and other animals work. It's the part of chemistry that focuses on the building blocks of life. Since life is kind of important to us humans, it's probably not surprising that organic chemistry has a lot of applications to our everyday lives. Every food that we eat is made of organic molecules. That's why our bodies need it. Many of the man-made products we take for granted today exist thanks to organic chemistry. The key thing to realize about organic chemistry is that a lot of the products we use in our lives come from plants and animals. Remember, something doesn't have to be currently alive to be an application of organic chemistry. For example, polymers are molecules with long chains. There are lots of polymers in our lives, from plastics to nylon to polycarbonate and acrylic. The structure of these man-made materials originally came from the natural world. Polymers are considered to be organic molecules. Rubber is probably the most famous natural polymer, which comes from the rubber trees. But even fully man-made plastics usually contain hydrocarbon molecules that originally came from plants and animals. Then, there is perhaps one of the most important things to human and the modern economy: petrochemicals. Oil and its products are really important in modern society. Oil gives us fuel for our cars, chemicals to make plastics, detergents, medicines, and dyes. So, how is crude oil an example of organic chemistry? Oil is created when dead animals and plants fall to the bottom of the sea, where they get covered with layers of sediment over millions of years. There, deep under the sea floor, oil is created through immense pressure and temperature. So, the reason that these are organic molecules is that they literally come from dead plants and animals. Maybe you're not a fan of oil because you don't like the damage it causes to the environment. Here's a question for you. Do you regularly wash your hands? Basic cleaning products like soaps and detergents are more important to society than you think. Cleanliness has improved the health of human beings over the last century. Soap and detergents are both made from organic molecules. Soap is made from animal fats, and detergents contain products that come from oil. Perhaps the most important application of organic chemistry is medicine. The advancements made in medicine have led human life expectancy to rise at a staggering rate. Since the human body is organic, a lot of the ways we make an ailing body healthy again must also be organic. Everything from antibiotics and painkillers to anesthetics and cancer treatments are made from organic molecules. Organic chemists are vital in the fight against all disease. Organic chemistry looks at molecules found inside living organisms. Not everyone enjoys studying organic chemistry, but it's super important to human society. It has numerous applications in our lives. The creation of polymers, like plastics and nylons, are applications of organic chemistry. Oil and everything that comes from it is also made up of organic molecules. In addition, cleaning products like soaps often come from organic materials, as do most medicines. Thus, organic chemistry is important for discovering new medicines, extending human lives, and is found in products all over the supermarket. Chemicals. Something we should all avoid, some people say. But if we actually avoided chemicals, we would perish within days. Let's discuss why. In a commonly repeated social experiment, a group of tricksters walk around a town telling people about the dangers of dihydrogen monoxide. People become very concerned. Dihydrogen monoxide is being put into almost every product in the supermarket. Something must be done. But it turns out that dihydrogen monoxide is just the chemical name for water. Indeed, Everything around you is made of chemicals, from the water you drink, to the food you eat, to the soap you wash your hands with. You couldn't survive without them. A chemical is simply defined as a compound that has been prepared or purified. And a compound is anything containing more than one element, more than one type of atom. So that's really all a chemical is, a substance made of more than one type of atom that has been somehow produced, put together, or made pure by removing other substances. So what do people really mean when they refer to the dangers of chemicals? They're usually talking about toxic chemicals. Toxic means the same thing as poisonous. It, in some way, causes harm or danger, especially to humans. People also use the word chemicals to refer to artificial chemicals, or chemicals made by humans. So, for the purposes of this lesson, let's focus on toxic and artificial chemicals found in the home. Since everything is made of chemicals, it's probably not surprising to find out that there are a lot of chemicals in the home. Even if we focus on chemicals found in bottles made by humans, there are still a lot. Chemicals are found in hand sanitizers, soaps, bleach, bathroom cleaners, shampoos, conditioners, moisturizers, shaving foams, sunscreens, and dishwasher tablets. The truth is that most of these things contain dozens of chemicals. So let's focus on a few of the most common ones. Ammonia is a chemical containing 1 nitrogen and 3 hydrogen atoms, bonded together. It was traditionally used in many household cleaners, though today it's still found in glass cleaner, all-purpose cleaners, and smelling salts. Sodium hypochlorite solution is a chemical found in anything considered to be bleach. It's also used to chlorinate swimming pools and in many dishwasher solutions or tablets, as it's great at killing bacteria and germs. Sodium bicarbonate is the chemical name for household baking soda. It's used to make cakes and other baked products rise in the oven. This happens because the chemical reacts with other ingredients to form carbon dioxide, which makes bubbles inside the mixture. Glycerol is typically found in soap. The chemicals found in soaps vary quite a bit, but in chemistry, a soap is defined as the salt of a fatty acid. A salt is the result of an acid and base neutralizing each other. So it's where a fatty acid is neutralized by a base. Glycerol is added to this for consistency and to prevent soap from drying out. Sodium lauryl sulfate is commonly found in detergent, which is generally the main ingredient of shampoo, which itself tends to contain a cocktail of chemicals, and laundry detergent. A detergent is a cleaning agent that's soluble in water and combines with dirt to make it soluble. In other words, it makes the dirt mix in with the water so that it can be removed. Detergents work well in hard water, whereas soaps do not. In shampoos and laundry detergents, the main detergent is typically sodium lauryl sulfate, but it may also be ammonium lauryl sulfate or sodium lauryl ether sulfate. Chemicals are compounds that have been prepared or purified. Chemicals are everywhere. After all, water is a chemical. But even when it comes to artificial and toxic chemicals, they're still found throughout our lives in our households. They're found in hand sanitizers, soaps, bleach, bathroom cleaners, shampoos, conditioners, moisturizers, shaving foams, sunscreens, and dishwasher tablets, among others. Some of the most common chemicals include ammonia, sodium hypochlorite, sodium bicarbonate, sodium lauryl sulfate, and glycerol. Ammonia is a chemical containing 1 nitrogen and 3 hydrogen atoms bonded together and is found in all-purpose cleaners and glass cleaners, while sodium hypochlorite is the main ingredient in bleach, and both of these kill germs. Sodium bicarbonate is baking soda and causes baked goods to rise in the oven. Soaps are salts of fatty acids that dissolve dirt, and the chemical glycerol adds consistency to soap. Detergents are similar to soaps, except that they work in hard water, where soaps struggle, thanks to sodium lauryl sulfate, which is commonly found in detergent.
When you hear the word chemistry, there are likely certain images that come to mind. Molecules, test tubes, the periodic table, maybe even some cool explosions in a movie. But chemistry is so much more than these things. In fact, chemistry is known as the central science because it touches all other natural sciences, like biology, physics, geology, and more. Chemistry is a physical science, and it is the study of the properties of and interactions between matter and energy. In other words, chemistry is a way to study the properties, characteristics, and physical and chemical changes of matter. Matter is pretty important because it's anything that has mass and takes up space. Basically all of the stuff that makes up our world. Chemists study atoms, which are the basic building blocks of matter, as well as interactions between atoms. They also study subatomic particles, which are smaller than atoms, and these include things like protons, neutrons, and electrons. Since everything on Earth is made of matter, and matter is made of atoms, you can see how this creates the overlap between chemistry and other sciences. You can't have stuff to study if you don't have stuff in the first place. In other words, matter really matters. Your understanding of chemistry may be shiny and new, but chemistry itself has been around for a very long time. Basic chemistry dates back to ancient times and is described as originating from alchemists who were very thorough scientists. They ran experiments and recorded their results, which is a key component of good science. Modern chemistry dates back to the 17th century, and credited as one of the founders of this scientific field is Robert Boyle. Boyle is one of the developers of this scientific method, which is an organized set of steps to gain knowledge and answer questions. Boyle believed in rigorous, tested experimentation and was a strong advocate of proving scientific theories before calling them truths. Though not always considered a formal science, chemistry has been performed throughout human history. People have been fermenting food and drink for centuries. Extracting metal from ores is another form of natural chemistry, as is making glass, soap, and extracting plant components for medicinal purposes. Archaeologists find pottery at their dig sites, and both the pots and the glazes used to protect them come from knowledge of chemistry as well. As you can see, chemistry exists whether we define it or not, and because an understanding of chemistry is so vital in so many other scientific fields, there are several different branches of chemistry that exist. In fact, chemistry is often studied so that scientists can better understand their own field. An exhaustive list of the different branches of chemistry would be, well, exhausting to go through. We only have so much time in this lesson, so let's focus on some of the major ones to give you an idea of how chemistry plays a role as a natural science. Analytical chemistry is a field that is just what it sounds like, the analysis of matter. Analytical chemists try to gain information and knowledge about the properties, composition, and structure of different materials and substances in order to better understand them. Applied chemistry is a neat field because it's the application of chemistry for practical purposes. You know all those different shampoos at the store? Some are for colored hair, some for dry, damaged hair, and others are for thin hair. Applied chemistry is specifically used to solve problems. In this case, chemistry is used to have different effects on different hair types. Biochemistry sounds a lot like biology and chemistry, and this is because it is chemistry as applied to living organisms and their processes. Metabolism, medicine, cellular biology, genetics, nutrition, and even exercise sciences are all types of biochemistry because they deal with the interactions of chemical, biological functions and structures. Environmental chemistry is a fast-growing field because this is the study of chemicals in the air, soil, and water. Environmental chemistry examines chemical reactions and their effects on our environment by understanding how the chemicals got there, how they're transported, and what happens to them once they're there. Even though chemistry is already a physical science, a specific branch of chemistry exists called physical chemistry. This branch applies physics to chemistry, which includes a whole host of its own branches. Things like quantum mechanics, nuclear chemistry, thermodynamics, and kinetics are all types of physical chemistry. As mentioned, this is just a small smattering of the different fields of chemistry, but we simply can't list them all here. But I bet that any scientific field you can think of probably has at least one chemistry field associated with it. Chemistry really is central to it all. Known as the central science, chemistry is the study of the properties of and interactions between matter and energy. Matter is stuff, and atoms are what make up that stuff. So you could say that chemists study all of the stuff on Earth as well as what that stuff itself is made of. Modern scientific chemistry dates back to the 17th century, but basic applications of chemistry go back much farther. This is easy to see when you think of how intertwined chemistry is with everything else and how many different branches of chemistry exist. Biology, physics, and even astronomy all have chemistry roots, and this is exactly why learning chemistry helps so many non-chemists be better scientists in their own field.
We construct the world around us by continually making observations about what we see. An observation is a phenomenon that can be witnessed and recorded. A set of observations can be used to make a hypothesis, which is a possible explanation for the observations made. But note, a hypothesis is just a possible explanation. Sometimes we get new evidence from an experiment or new observations that contradict our hypothesis. An experiment is a procedure carefully done to examine the validity of a hypothesis. In fact, scientists seek to test their hypotheses by making extensive observations or conducting many experiments. The idea is to prove a hypothesis by trying to disprove it first. A hypothesis can be changed or reformulated over a series of observations or experiments. Once a hypothesis holds true, it is accepted as fact. Over the course of time, a collection of hypotheses can be used to generate either a scientific law or theory. A scientific law is a statement that summarizes a collection of observations or results from experiments. Scientific laws are always true under the same conditions and therefore can be used to make predictions. In fact, our cartoon friend here could use some of the laws of inheritance to better understand why some cats are gray, while other cats are orange, black, white, or even calico. In case you've never heard of them, the laws of inheritance were developed by the Austrian monk Gregor Mendel to explain inheritance patterns initially observed in pea plants. Collectively, the laws explain how genes are passed from parents to their offspring. Because Mendel's explanations were true for a variety of organisms, they became a set of laws. A scientific law may also be referred to as a principle. Other examples of scientific laws or principles include the law of conservation of mass, Coulomb's law, Newton's law of universal gravitation, the ideal gas law, Bernoulli's principle. A theory or model is also based on a set of hypotheses. Unlike a law, however, a theory describes and explains why a natural phenomenon occurs. In science, theories explain reality well and are generally accepted as truth. Theories are based on information from many different areas of study. Our cartoon friend might find the theory of evolution quite helpful when trying to understand where cats come from, or why different colored fur might be beneficial in helping cats to survive. To briefly summarize, the theory of evolution explains that organisms slowly change over time due to genetic mutations. Organisms that have beneficial mutations, like the ability to camouflage well, are more likely to survive and pass their traits on to their offspring. Theories let scientists make testable predictions. Theories can also be changed or modified if new evidence is found. Examples of theories include cell theory, theory of relativity, atomic theory, plate tectonics theory. To better understand the relationship between our three main ideas, hypothesis, law, and theory, let's compare them to an old, strong structure that has withstood the test of time, the Parthenon in Greece. The Parthenon has three fundamental parts. The foundation is the ground structure on which the entire structure is built. The columns are tall pillars built upon the foundation. Together, all of the columns support the weight of the roof, which is used for protection. In science, our collection of hypotheses represents our foundation. Our columns are the theories and laws we have developed using our hypotheses. Our columns are all equal in strength and importance. Together, the columns support our understanding of the universe, which is the roof of our structure. As time goes on, additions or modifications are made to the structure as we discover new information or need to repair old ideas. We have established that hypotheses are essential to making scientific laws and theories. Hypotheses are based on observations and verified through experiments or more observations. Sets of hypotheses are used to generate scientific laws or theories. Both, in turn, are used to make predictions and generate experiments. If the results contradict the predictions, the theory or law is modified and the process is started again. For scientific laws, the process rarely occurs. Let's make a Venn diagram for scientific laws and theories to understand how they are the same and how they are different. If you've never used a Venn diagram before, they are constructed by making a circle representing each idea. Characteristics or qualities of each idea are listed inside. Circles for related ideas are then made to overlap each other. Shared characteristics are placed in the area of overlap. Unique characteristics are left outside of the overlap. If you want a challenge, pause the video now and make your own Venn diagram for scientific laws and theories. Resume playing when you are finished to compare your work. Theories are used to explain why natural phenomena occur. Laws are used to summarize a set of observations about natural phenomena. Both laws and theories are based on hypotheses. They can be used to make predictions, and both can be revised if necessary. An observation is a phenomenon that can be witnessed and recorded. A hypothesis is a possible explanation for the observations made. An experiment is a procedure carefully done to examine the validity of a hypothesis. A scientific law is a statement that summarizes a collection of observations or results from experiments. A theory describes and explains why a natural phenomenon occurs. Hypotheses are based on observations and verified through experiments or more observations. Sets of hypotheses are used to generate scientific laws or theories. Both scientific laws and theories can be used to make predictions and generate experiments. If the results contrast with the predictions, the theory or law is modified and the process is started again.
Recall from a previous lesson that everything around you is matter, and that matter can have physical properties and chemical properties. Just like matter can have physical and chemical properties, it can also undergo physical and chemical changes. A lot of times in chemistry we show a change by using an arrow. The stuff we started out with goes on the left side of the arrow, and the stuff we created is shown on the right side of the arrow. When you boil water, what do the bubbles contain? Hot air? Oxygen? Water vapor? Don't feel bad if you don't know the answer. This is a question that often gets answered incorrectly. To answer it, we would first need to determine what is happening to the particles in the water. When you add energy to the particles of a substance by heating it on a stovetop, it causes the temperature to increase, which means that the particles are moving faster. If they get moving fast enough, the temperature will eventually stop increasing and the bubbles will start forming. You have just reached the boiling point. If the temperature stops increasing, then where is all that extra energy going? It is being used to turn the liquid water into steam, or water in the gas phase. So what you're seeing inside of those bubbles is really just water vapor. This transition from a liquid to a gas is called a phase change. A phase change is the transition from one state of matter to another. You may already know the three common states of matter: solids, liquids, and gases. Solids have a definite shape and volume, meaning that for the most part they keep their shapes and they can't be compressed. If you were to add energy to a substance in the solid state, it would turn into a liquid. This is called melting, and the reverse process is called freezing. Liquids have a definite volume, but not a definite shape, which means that they will take the shape of their container, but like solids, they're not compressible. Hydraulics and car brakes work because liquids are incompressible, but they are still able to flow. Now, if we were to heat this liquid enough, it would turn into a gas. This is called vaporization, and the reverse process is called condensation. You may notice on a warm day water droplets form on the outside of a cold drink. This is what happens when water vapor in the air cools down after coming in contact with your cold beverage. Gases do not have a definite shape or a definite volume. They will take the shape of their container, and they can be compressed. So back to the bubbles in the boiling water. We now know that they are filled with water vapor. But why do they rise to the surface? Gases are a lot less dense than liquids, so they rise to the surface of a liquid. All of these transitions I just discussed are phase changes, meaning that the particles still have the same composition, ice, water, and steam are all H2O, but they are in a different state. Phase changes are examples of a larger category of changes called physical changes. A physical change does not affect the composition of a substance. Other types of physical changes include changes in form. For example, when you crush a can, sharpen your pencil, or cut a piece of paper, you're not changing what it was you started out with, you're just changing its form. You still have the same atoms and molecules connected in mostly the same way. Even magnetizing a paperclip is an example of a physical change. So what if you take that piece of paper you just cut and you set it on fire? Do you still have paper? If you burn paper, what you are going to produce still has the same atoms as the original paper, but they are rearranged and will create entirely new substances with completely different properties. This type of change is called a chemical change. A chemical change is a change that involves a transformation into a new substance. Often we will call these chemical reactions. Examples of chemical changes include rusting iron, baking a cake, digesting your lunch, and tarnishing silver. One thing to remember about both types of changes is that when they occur, the amount of matter and the number of atoms you started out with will always stay the same. Physical and chemical changes will never cause a change in the amount of matter you end up with. For example, when you are boiling water, the water level may go down, but your water isn't disappearing, it's just being converted to another form, steam. Also, after you're done burning a campfire, it may look like all you have left with is ashes and something along the way disappeared. Really, what happened is you created a lot of carbon dioxide, which was released into the atmosphere. Matter was not actually destroyed in this process. So to summarize all of this information, matter is constantly changing around us. There are two major types of changes, physical and chemical changes. Physical changes can either be changes of state, changing among liquids, solids, and gases, or changes in form, like cutting, smashing, or bending. Either way, what you will end up with will have the same composition as what you started with. If matter undergoes a chemical change, the atoms will rearrange and form completely new substances with different chemical formulas and different properties, like when a plant uses sunlight, water, and carbon dioxide to produce carbohydrates and oxygen. In both a physical and chemical change, matter is conserved, meaning that during the process, particles are neither created nor destroyed.
If you've studied chemistry for some time, you've probably noticed that it has a lot of properties that are used to define matter. Throughout introductory chemistry, you solve problems looking at mass, number of moles, melting point, densities, and several other variables that will affect the system you're studying. You may have noticed that some of these properties are more intrinsic or unique to the specific substance being examined. These unique properties are also known as intensive properties. Intensive properties are properties of matter that do not change when you vary the amount of matter. Other properties, such as mass, will vary depending on the amount of matter. These properties are called extensive properties. You can remember the difference by thinking about the fact that extensive properties are directly affected by the extent of the substance, or how much matter you have. Intensive properties are more intrinsic or essential to the nature of the substance. We're going to look into a few examples to better understand these distinctions. Let's first start with extensive properties, or those that rely on the amount of matter. If you have 200 grams of water in a glass and pour out half of the glass, you now only have 100 grams. This is because you have gotten rid of half of the amount of matter in the system. In much the same way, if you have a liter of water and pour out half, you now only have half of a liter. Extensive properties are those properties that deal with the amount or answer any of the how much questions. Can you think of any other examples that are extensive properties? An obvious one may be the number of moles. Many chemistry problems will ask you to solve the number of moles in a specific amount of matter. Since this is a how much type of property, you can easily identify it as an extensive property. There are only so many ways in which you can define the amount or extent of matter. What about all of these other properties that we use to describe matter? The remainder of these are intensive properties, or those that do not change when you change the amount of matter. Remember when we poured out half of the glass of water, decreasing the mass from 200 grams to 100 grams? If the water started at 20 degrees Celsius, the water would have stayed at 20 degrees Celsius, even when we removed half of the matter. This behavior helps us identify temperature as an intensive property. You may have learned earlier that water freezes at 0 degrees Celsius. Whether we are talking about a lake or just a glass of water, both will freeze once the water reaches 0 degrees Celsius. You may be thinking, but wait, it will take a lot longer to freeze a lake rather than a glass of water. However, the freezing point is not concerned with the amount of time it takes to reach a certain temperature, but rather just describes the behavior that water will transition from liquid to solid at 0 degrees, regardless of the amount of matter. Thus, freezing point is an intensive property and doesn't change when we vary amount. Other examples of intensive properties are color, boiling point, pressure, molecular weight, and density. Density is an interesting example. Remember that density is mass divided by volume. As you just learned, both mass and volume are extensive properties, or dependent on the amount of matter. So how is density an intensive property if it's just the ratio of two extensive properties? Well, it turns out that when we take a ratio of two extensive properties, you get an intensive property. When you poured out half of the glass of water, the density stayed at just 1 gram per cubic centimeter. By pouring out half of the water, you decrease the mass and the volume by half. Remember that when something is on both the top and the bottom of a fraction, they cancel each other out. In this case, you are multiplying both the top and the bottom of the fraction by 0.5. Thus, 0.5 cancels out in both cases, and the density remains the same. Extensive properties do not reveal much about what the substance actually is. For instance, if I were to tell you that a substance weighed 100 grams, it would be nearly impossible for you to correctly guess what that substance is, because anything can be 100 grams. Instead, if I were to tell you that a substance had a boiling point of 100 degrees Celsius, you would likely be able to guess that that substance is water. This is because very few substances besides water have a boiling point of 100 degrees Celsius. Thus we characterize matter by its intensive properties. You may see these variables listed in chemistry books to describe substances. We cannot define the general characteristics of matter by their extensive properties because these vary with the amount of matter. I can describe water generally as having a freezing point of 0 degrees Celsius, a boiling point of 100 degrees Celsius, and a density of 1 gram per cubic centimeter. In fact, if I told you all of these intensive properties, you'd be able to tell me that I was talking about water. But I cannot generally define water as having a volume of 1 liter. This is because water is still water, regardless of whether it has a volume of 1 liter or 1 million liters. Let's review. In this lesson, we discussed the differences between intensive and extensive properties. Extensive properties are properties that vary with the amount of matter, and intensive properties do not. Thus, extensive properties are those that help us define how much matter we have. For example, mass, volume, and the number of moles are all extensive properties. Intensive properties are more intrinsic to the matter being discussed. For instance, the boiling point of a substance will not vary depending on how much of it you have. Water will boil at 100 degrees Celsius whether we have 1 liter or 50. Because intensive properties do not change with the extent of matter, these properties are used to characterize the different types of matter.
Think back to the last time you ate some jelly beans. Were you selective about which colors you ate? Whenever I'm eating jelly beans, I go for the green ones first. Just like the mixture of jelly beans, most substances are mixtures of things. Remember that there are two types of matter that exist: pure substances and mixtures. A mixture is a physical combination of two or more substances that are mixed but not chemically combined. The components of a mixture maintain their own physical properties. An example of a mixture is salt water. If you were to drink salt water, it would taste like water with salt in it. Mixtures come in two main types: homogeneous and heterogeneous mixtures. A homogeneous mixture is a mixture that is uniform throughout, meaning that one part of it has the same distribution of ingredients as another part. A heterogeneous mixture is a mixture that is not uniform throughout, meaning that there is an unequal distribution of the ingredients of the mixture. Air is a homogeneous mixture of many different gases, including oxygen, nitrogen, carbon dioxide, and water vapor. I know it is homogeneous because each breath I take will contain nearly the same ratio of ingredients. Homogeneous mixtures are sometimes called solutions, especially when it is a mixture of a solid dissolved in a liquid. An example of a heterogeneous mixture is a chocolate chip cookie. It contains sugar, chocolate chips, butter, eggs, and flour. Each bite I take is likely to contain a different amount of chocolate. Heterogeneous mixtures are easily distinguished because their different components can be seen as individual substances, whereas a homogeneous mixture all looks the same. The rest of this lesson is going to go into detail on a few of the many ways a mixture can be separated into more individual ingredients. The first and most obvious way to separate a mixture is to manually separate it. This is probably what you did when you had a bag of jelly beans and picked out which color you wanted to eat. My next example involves a mixture of salt, sand, and iron filings. All of the particles in this mixture would be about the same size. So how would you separate them? Would you take a tweezers and separate them all out? This may get a little time-consuming, so one thing you may want to do is use a magnet. This uses magnetism to separate out the iron. So now the iron is out. How would you separate the salt and sand? To figure this one out, we need to look at some of the physical properties of salt and sand. You may have noticed that salt has the ability to dissolve in water, where sand does not. So I would add some water to this mixture and try to dissolve all the salt, leaving the sand to sink at the bottom. Our next technique is filtration, and it's one of the most common methods for separating a mixture in a chemistry classroom. When you brew coffee, you may rely on a coffee filter to keep the grounds from getting in your drink. If our salty water and sand mixture is poured through a filter, the salty water would go through, leaving the sand behind. Last on our list is separating the salt from the water. There are two ways we can do this. The first is evaporation. It may take some time, but eventually the water will evaporate, leaving the salt behind. This is sometimes called crystallization, because the solid salt will form crystals as the water evaporates. If you're short on time, you may want to take advantage of the boiling point of water, which is much lower than the boiling point of salt. By heating the water to its boiling point, you're allowing it to change from a liquid to a gas, eventually leaving all of the salt behind. This process is known as distillation, and it's used in the purification of all kinds of things, from water to crude oil. For our last example, we're going to go back to the jelly beans. Did you know that most dyes to make candy are actually mixtures of different pigments? The same is true for dyes that are used in markers and ink pens. Is it possible to separate the pigments of jelly beans or markers? You may know the answer to this if you've ever spilled water on a document and watched the ink bleed into different colors. What you are seeing is a separation of the pigments of ink because each pigment has a different attraction to the water based on subtle differences in each pigment's polarity. Chemists use these small differences to separate some mixtures using chromatography, which means color writing. In paper chromatography, a small dot of the ink or dye to be separated is placed near the bottom on a piece of superabsorbent paper. Let's look at my green jelly beans. If I were to dissolve a little of the outer green layer of the jelly bean in water and put a little dot of that green dye on a piece of chromatography paper, it may look something like the middle dot in this picture. The paper is then put in a container with a small amount of solvent, maybe vinegar or ethanol. Can you picture what happens to one end of a piece of paper when it's touched to some water? The paper draws up the water in a process called capillary action. As the paper is absorbing the water, some of the water mixes with the dot of dye that informs a solution with the water traveling up the paper. This green has now separated into two different colors, yellow and blue. The attraction that the dye has with the paper will determine how far the dye travels up the paper. Dyes that are more attracted to the paper won't travel up as high, and dyes that are not as attracted to the paper will travel up the highest. Once the solvent reaches the top of the paper, the line where it finishes is marked, and the chromatograph is removed and allowed to dry. The distance that each dye travels is measured from the starting point, and a value called a retention factor is calculated. The retention factor, or RF, is the distance the dye travels compared to the total distance the solvent traveled. So in this example, we would calculate the RF for the blue dye by taking the distance between points 1 and 2 divided by the distance between points 1 and 4. Notice that you will never have a retention factor that is more than 1 because the dye cannot travel farther than the solvent carrying it. Also, the RF does not have any units, because if you take a unit divided by the same unit, they both cancel out. Chromatography can be related to a school bus at the end of the day. After school is let out, all of the students get on the school bus. Then, as the bus drives around, kids are let off when the bus stops at their stop. Of all the separation techniques you may be asked about, chromatography is the most complicated, and in paper chromatography, it relies on the differences in attractions between the mixture components and the paper or solvent you use. Distillation is a way to separate mixtures based upon differences in boiling point, usually to separate two different liquids that formed a solution. Evaporation and crystallization are separations based on the ability of one substance to evaporate easily, usually water, and another substance that does not readily evaporate, usually a salt. The simplest of the separation techniques include using a magnet, manually separating, and filtering.
If you've ever made hot tea in a clear glass, you've observed that the tea grows darker the longer you leave the tea bag in the water. As the tea gets darker, less light is able to travel through the glass. In this example, the strength of the tea, or its concentration, is directly related to how much light travels through the glass. When incident light hits a substance, part of the light is transmitted through the substance and part is absorbed by the substance. Incident light is another term for incoming light. The incident light shining on an object is either reflected, transmitted, or absorbed. Transmittance is the fraction of light that passes through a substance. Absorbance is the measure of light that is absorbed by the substance. The fraction of light that is reflected is normally very small, so we will ignore this fraction for simplicity. So if 80% of light is transmitted through a liquid, 20% of the light is absorbed by that liquid. Beer's law is an equation that allows scientists to relate the decrease of light intensity to the concentration of a substance. Before we learn the equation, we first must understand the concepts of cell path length and analyte concentration, which are both used in Beer's law. Cell path length is the two-dimensional distance that light travels through in the sample. Imagine we have a light source facing a light detector. If we place our glass of tea in front of the light source, some of the light is absorbed by the tea, so less light reaches the light detector. The length across the tea in the glass is called the cell path length. If we place another glass of tea in front of the light source, even less light reaches the light detector. In this case, you have doubled the cell path length, which decreases the transmittance. This effect explains why tea will look lighter in a glass than a larger pitcher, because the pitcher is larger and the cell path length is larger. The other concept we must understand is analyte concentration. The analyte is the substance that we are interested in measuring in Beer's law and what is absorbing the light. Concentration in chemistry is the amount of solute in the total volume. If we are adding food coloring to a glass of water, the color will get darker the more food coloring you add. In this case, we are increasing the solute, which is increasing the concentration of food coloring in water. Beer's law relates the attenuation of light to the concentration of a substance across the cell path length. The equation is A equals epsilon times L times C, where A is the absorption of light, epsilon is the molar absorptivity, L is the cell path length, and C is concentration. Molar absorptivity is how strongly a particular substance will absorb light across a given length. As you see from this equation, the absorption of light by a substance is directly proportional to its concentration, cell path length, and the known molar absorptivity of the substance. Going back to our tea example, if you increase the cell path length by adding another glass in front of the light, this will increase the absorption and allow less light through. If you increase the concentration of tea in the water, this will also increase the light absorption. If you substitute a substance with a higher molar absorptivity, perhaps like coffee, more light will get absorbed as well. Scientists use this relationship to measure the concentration of a substance. They will place the substance between a light source and a light detector. The absorptivity is determined by the percentage of light that is received at the light source. Remember that this is the amount of transmitted light. If 30% of the light is transmitted through the substance, this means that 70% was absorbed. Scientists can measure the cell path length easily, and molar absorptivity is a known quantity. This allows them to easily solve for the concentration. In summary, Beer's law relates the analyte concentration, molar absorptivity, and cell path length of a substance to the absorptivity, which allows scientists to use light to understand the analyte concentration. The majority of light traveling through a substance is either transmitted or absorbed. The distance that light travels through the substance is known as cell path length, and it is directly correlated with absorptivity. The longer the cell path length, the higher the absorptivity. Molar absorptivity is a known quantity of how strongly a particular substance will absorb light. For instance, coffee has a higher molar absorptivity than tea. Scientists will use these measurable quantities and the absorptivity of the unknown substance to solve for the concentration using Beer's law.
I have always heard that you should never compare apples to oranges. So I'm going to start off this lesson by comparing apples to apples. Later on, this may help you remember how to compare and contrast different isotopes of atoms. So, more specifically, we are going to describe 3 different types of apples: the crab apple, the golden delicious, and the Granny Smith. All very different, but all still apples. So, what makes them apples? They're all biologically named Malus domestica. They grow on trees, they have stems, the list goes on. But what makes them different? First of all, the crab apple is very small. It's red in color and it tastes quite sour. And for the purposes of this lesson, we are going to give it a fictional mass of 1 AMU, which we'll call the apple mass unit. Whereas the golden delicious is medium-sized, yellowish in color, tastes sweet, and we're going to give this a mass of 2 AMU. Finally, the Granny Smith is large, green, and tastes sour. We will give this apple a mass of 3 AMU, so it weighs 3 times as much as the crab apple. They're all similar in that they're apples, but they have many different characteristics. So if I were to ask you, what is the mass of an apple, what would you say? 1 AMU, 2, or 3 AMU? Well, it all depends on which type of apple you're referring to. Now let's compare atoms. In a previous lesson, you learned about the makeup of the nucleus and how it contains both protons and neutrons, both of which are the primary contributors to the mass of the atom. The mass of the electrons is not significant enough to keep track of. The number of protons an atom has will determine which type of element it is, and all atoms of the same element will always have the same number of protons. Where things get interesting is in the number of neutrons in the nucleus. We're going to use hydrogen as our example. Hydrogen has 3 major isotopes. Remember that isotopes have the same number of protons, but different numbers of neutrons. The most common isotope of hydrogen has only 1 proton and 0 neutrons. If both protons and neutrons have a mass of about 1 AMU, atomic mass unit, the mass of this atom would be about 1 AMU, just the mass of the proton. This isotope of hydrogen has a special name, protium, and it makes up over 99.98% of all hydrogen atoms. The next most common isotope is called deuterium. Its nucleus contains 1 proton and 1 neutron, so it has a mass of about 2 AMU, 2 atomic mass units. It makes up less than 0.02% of the population of hydrogen atoms. The last isotope is called tritium, and it has, as you may guess, still only 1 proton, but it contains 2 neutrons in the nucleus, giving it a mass of 3 AMU, 3 atomic mass units. There is very little tritium that exists, and it's very unstable. So if I were to ask you, what is the mass of a hydrogen atom? You would need to know which isotope I was talking about, protium, deuterium, or tritium. Remember that these 3 isotopes are all chemically the same, just like our 3 different types of apples are all just apples. They're all still hydrogen atoms, and they will all react the same way. For example, you may know that water, H2O, is made up of 2 hydrogen atoms and 1 oxygen atom. What you may not know is that although most of the water you drink contains the protium isotope of hydrogen, there are a few molecules in your glass that will contain the heavier deuterium isotope. Does this matter? Not really. Our bodies contain a small percentage of heavy water, and we are okay. We wouldn't want to make a practice of drinking 100% heavy water on a daily basis, though. This special heavy water is used in some nuclear reactors and some scientific laboratories. Now I'd like to focus your attention to the periodic table. More specifically, the hydrogen block at the top left corner. See that little number below the chemical symbol? That is called the average atomic mass, or the atomic weight. Remember, the units for atomic mass are AMU, or atomic mass units. So which isotope's mass are we seeing? Protium, deuterium, or tritium? The answer is all of them. The atomic weight on the periodic table is calculated based on the relative abundances of each isotope of that element. It is really a weighted average of all of the naturally occurring isotopes. So because most of the hydrogen has a mass of 1 AMU, the atomic weight on the periodic table is going to be very close to 1. However, because there is a teeny bit of heavier hydrogen isotopes, the weight represented will be slightly higher than 1, or 1.0079 AMU. Another example is lithium. There are 2 major isotopes of lithium. Lithium-6, which has 3 protons and 3 neutrons, and lithium-7, which has 3 protons and 4 neutrons. According to the periodic table, the atomic weight is 6.941 AMU. Based on this, which isotope do you think is most common? Lithium-6 or lithium-7? Because the number 6.941 is much closer to 7, there is likely to be much more lithium-7 that exists in nature. Keep in mind, just like the apples and the hydrogen atoms, both of these lithium isotopes will have similar behaviors. Their only difference is their mass. Because most of our calculations will be dealing with the general population of atoms and not specific isotopes, we will be using this atomic weight value in most of the lessons in this course. So it's important to know how it's calculated and what it really means. Also, keep in mind each periodic table may look different from the next, so be sure to orient yourself before you start making calculations. Isotopes are just variations of the same element. They have the same number of protons, and they will all react the same way. The only difference is they have different numbers of neutrons, which will make their masses different. The abundance of each type of isotope is taken into account when calculating the average atomic mass, or the atomic weight, which is found on the periodic table. What images come to mind when you hear the words nuclear radiation? Most likely these words conjure up a graphic scene of three-eyed fish and glowing green ooze. There are many misconceptions flying around out there when it comes to nuclear radiation, and the best thing you can do is educate yourself on the subject. Who knows, someday you may be voting on whether a nuclear facility is built near you. Did you know that less than 1% of all the radiation you are exposed to comes from the nuclear industry? Most of it comes from natural sources like rocks. You are even a little radioactive. Nuclear radiation comes from all kinds of different places. There is natural radiation from the sun, water, and even bananas. There are also man-made sources of radiation, like nuclear reactors, certain types of medicine, and the smoke detectors in your home. What exactly is radiation, and how damaging is it? The amount of danger nuclear radiation presents depends on which type of radiation it is. Today we will be discussing the three most common types of radioactive decay: alpha, beta, and gamma. Before we do that, we'll first do a quick review of the nuclear particles you should be familiar with, along with their nuclear notation. As you may recall, the two particles that are found in the nucleus are the protons and neutrons. Because the atomic number of an element is the number of protons its atom has, a proton essentially has an atomic number of 1. It also has a mass number of 1 because its mass is almost exactly 1 AMU. These two numbers are so important that sometimes they are included in certain notation. For example, when we are distinguishing the difference between 3 carbon isotopes, notice they all have 6's on the lower left of the symbol. Those 6's represent the number of protons, or the atomic number. They all have the same atomic number because they're all carbon. The top number is the mass number, which is the number of protons and neutrons, because both protons and neutrons have a mass of 1. Each of these 3 isotopes has the same number of protons, but different numbers of neutrons. Particles in the nucleus can also be represented by this nuclear notation. Going back to the proton example, with its atomic number of 1 and mass number of 1 can be represented a couple of different ways. Sometimes as a P with the atomic number on the bottom and the mass number on the top. Sometimes a little plus is put in front of the P indicating its charge. And sometimes it's even represented as a hydrogen nucleus with an H instead of a P, because most hydrogen atoms have an atomic number of 1 and a mass number of 1. When using nuclear notation, the neutron is almost always represented as a 1, 0, and N. The 1 indicating the mass number, the 0 showing the atomic number, and the N symbolizing that the particle is a neutron. Later on you will see why representing particles like this helps us keep track of everything. Now let's move on to the most common types of nuclear decay. The first is alpha decay. In alpha decay, the nucleus emits an alpha particle, or a particle containing 2 protons and 2 neutrons. The nucleus is said to decay or change into one that is a little lighter, one with 4 less particles. An alpha particle can be represented a couple of different ways. First, with the 4, 2, and alpha symbol, the 4 representing the mass number, the number of protons plus neutrons, and the 2 representing the atomic number, the number of protons. Instead of the alpha symbol, the symbol for helium is sometimes used, because it's really just a helium nucleus. Alpha particles are relatively heavy and quite slow-moving. It is for this reason that they can be blocked very easily by air, paper, clothing, and even your skin. Ingesting an alpha particle emitter would be dangerous because your inner tissues don't provide the protection that your skin does, and the alpha particles could cause some tissue damage. One of the main sources of alpha particles is the element radon, which is a gas found in many rocks. If a lot of radon is inhaled, it can get in your lungs and damage lung tissue. Some homes are even equipped with radon detectors to warn you if the levels are getting too high. Next up is beta decay, or beta-minus decay. Beta decay occurs when a neutron turns into a proton and an electron is emitted. It can also be represented a couple of different ways. Both have a 0 and -1, and either a beta symbol or an E is shown. The reason an E is used is because a beta particle is really just a high-energy electron being emitted from a nucleus. Beta decay occurs when the nucleus contains too many neutrons. For example, tritium, the super heavy isotope of hydrogen, has 2 neutrons and 1 proton. The most common form of hydrogen contains no neutrons. This tritium isotope is very unstable, and it will likely undergo a beta decay, turning into a helium atom because one of its neutrons transforms into a proton and releases an electron. Unlike alpha particles, beta particles are high energy and very light. They can travel through paper and certain types of clothing, but they're usually stopped by the first couple of layers of your skin. To shield beta particles, a sheet of aluminum is needed. They can cause tissue damage, which is both good and bad. Damaging healthy cells can cause cancer. However, when beta particles damage cancer cells, they can provide a cure for cancer. Finally, we have gamma decay. Gamma decay occurs when the nucleus of an atom is very high in energy. Just like electrons move out to higher energy levels, protons and neutrons can exist in higher energy levels as well. Also, like electrons, when these particles fall back down into lower energy levels, radiation is released. When it is released from the nucleus, by having protons and neutrons falling back down, very high energy gamma rays are released. Gamma rays are symbolized by a 0, 0, and a gamma symbol. Notice how both the atomic number and the mass number are 0. This means that this is a particle that contains no mass. It also doesn't change the atomic number of an element because the only thing that changes is that the nucleus loses energy. The structure of the atom is unchanged. Blocking a gamma ray is a lot more difficult. It requires a thick layer of lead to absorb the radiation. Gamma rays are very dangerous when in contact with high quantities of them, and they can cause a lot of internal damage because they're able to pass through the body. If in contact with large quantities of gamma rays, internal cell death can occur. On a positive note, gamma rays are often used to sterilize medical equipment, and, just like beta particles, they can aid in the treatment of certain types of cancer. As I previously mentioned, there is no way to escape radiation completely, and it wouldn't make any sense to walk around in lead clothing. What you can do is learn about the sources of radiation and the different forms of radiation so you are more educated on some of the issues that make their way into the news, and so you can be a more informed citizen. Altogether, there are 3 major types of nuclear decay that radioactive particles can undergo: alpha, beta, or gamma decay. Each type emits a particle from the nucleus. Alpha particles are high-energy helium nuclei containing 2 protons and 2 neutrons. They're heavy and can be stopped by as little as a piece of paper. In beta decay, a neutron in the nucleus transforms into a proton and releases an electron, the beta particle, which is much lighter but requires a minimum of aluminum to shield it. Finally, gamma rays are emitted when the nucleus has too much energy. They have no mass, and they require lead to stop them. Imagine you're getting settled in to watch the new action film at your local theater. You have a big tub of popcorn on your lap, and you're sitting back and watching as the previews begin. About 15 minutes later, the previews finish up, and you notice half of your popcorn is gone. It must have been good. The movie starts and you slow down your eating a little. But 15 minutes after the movie has started, you ate half of what you had left and are now down to a quarter of your popcorn. This continues for the rest of the movie until all of your popcorn is gone. If we were to graph your popcorn eating during the movie, it may look something like this. You may notice a few things about this graph. First, your popcorn eating did not happen at a steady pace. If that were the case, it would look more like a straight line. What it shows is that you ate faster at the beginning than at the end, because more popcorn is consumed in the first 15 minutes than in the second 15 minutes. The second thing you may notice is that every 15 minutes you eat half of what you had. This phenomenon takes place every day in many chemical reactions and nuclear reactions, and it is called the half-life, which is the amount of time it takes for half of the sample to react. Your popcorn had a half-life of 15 minutes, meaning that every 15 minutes, half of it will get eaten. Just like your popcorn, radioactive particles have half-lives. Let's take an example. Say we have a bunch of cobalt-60 atoms. Cobalt-60 decays down to nickel-60 during beta decay. But how do we know when the cobalt-60 atoms are going to decay? Are they all going to decay at once or randomly? Initially, it may seem like atoms decay randomly, but their probability of decaying can be predicted using an atom's half-life. It turns out that the half-life of cobalt-60 is about 5.27 years. That means if I start out with 16 cobalt-60 atoms and I wait 5.27 years, I will probably be left with 8 cobalt-60 atoms and 8 nickel-60 atoms. Then, if I wait 5.27 more years, half of the 8 cobalt-60 atoms that were left should decay, giving me only 4 cobalt-60 atoms, and a total of 12 nickel-60 atoms. 5.27 years after that, half of the cobalt that remained will decay into nickel-60, giving me 14 atoms of nickel-60 and only 2 atoms of cobalt-60. If I wait another 5.27 years, half of those 2 remaining atoms, so 1 atom, should decay, giving me a total of 15 nickel-60 atoms and 1 lonely little cobalt-60 atom. Now, we can never have half of an atom, so what happens next? This is where probability makes more of a presence. If I wait 5.27 more years, there is a 50% chance that the 1 remaining cobalt-60 atom will decay. It either will or it won't. If it does, then all of the atoms will have decayed. If it doesn't, then it has a 50% chance of decaying in the next 5.27 years. One thing that is really neat about half-life is that it can be simulated very easily. All you need is a bunch of pennies, or any other type of coin, and a clock or stopwatch. We're going to assign a half-life of 30 seconds to this made-up radioactive element. First, write down how many coins you have. This will be our initial amount. Now, wait 30 seconds. As you're waiting, shake up the coins in a container or in your hands so they get all mixed up. When the 30 seconds has passed, dump your coins on a table and remove all the heads. This should leave about half your coins. The heads represent decayed atoms, and they will no longer be part of our sample. Write down how many remain and shake the remaining coins for another 30 seconds. Again, after 30 seconds have passed, dump your coins on a table and remove all of the heads. Write down how many remain, and continue this process until all of your coins have decayed. Notice at the end how you can never have half of a coin? So when you're down to just 1 or 2 coins, you can see the probabilistic nature of them decaying. You may end up shaking 1 coin for many 30-second half-lives because it just won't decay. Or you may be down to 4 coins and all of them come up as heads. You should quickly see that there is no way of being able to predict exactly what will happen during each shake, but you can make good predictions about what should happen. In fact, if you were to graph your results by putting the time on the x-axis and the number of radioactive coins on the y-axis, you should almost always end up with a graph that looks like this. In nuclear reactions, most likely instead of starting out with 16 atoms or even 100 atoms, you would be measuring the amount you have in grams, or some other mass unit. The same rules still apply. If I start out with 20 grams of carbon-14 and wait about 5,730 years, the half-life of carbon-14, around 10 grams will remain, and 10 grams will have been converted into nitrogen-14. That's the product of a carbon-14 atom that underwent beta decay. This is how carbon dating works, and it's used to determine how old an artifact is. Scientists measure how much carbon-14 is left in a sample, and they are able to estimate how many half-lives it went through. This will allow them to get an approximate idea of how old the material is. You are surrounded by radioactive isotopes. However, many don't pose much of a threat because they have such long half-lives. The half-life of a radioactive isotope is the time it takes for half of the sample to react or decay. This time can range anywhere from a portion of a second to thousands of years, depending on the identity of the starting isotope. Nuclear chemistry is a field of chemistry that deals with the use of radioactive isotopes and other nuclear reactions. Nuclear reactions provide us with enormous amounts of energy. Radioactive isotopes are used to determine the age of old artifacts, diagnose disease, and treat certain types of medical conditions. In this lesson, we are going to take a closer look at each of these applications of nuclear chemistry. What can the sun do that we can't? The answer is run on nuclear fusion. Nuclear fusion occurs when two or more atoms fuse together to form a single, heavier atom. Keep in mind that during this process, not all of the mass is conserved. The heavier atom that is produced is actually lighter than the two individual pieces, which means that mass is lost. And because mass and energy are tied together, when mass is lost, energy is lost or emitted. In a fusion reaction, massive amounts of energy are emitted. Currently, there is no feasible way to harness this energy from fusion and use it to power our infrastructure, but several years down the road, it is possible that it could supply us with the energy we need. In a way, we are able to use some of the energy from fusion reactions. The sun is essentially a fusion reactor, creating energy by fusing hydrogen atoms together to form helium, and the sun is our primary source of energy. We use the sun's energy for solar power, photosynthesis, and even in the fossil fuels we burn. Fossil fuels are really just dead organisms that once used the sun for energy and that have been under a great deal of pressure by being buried under rocks. So right now, on Earth, we can't run our own nuclear fusion reactors, but we still rely heavily on the fusion reactions that take place on the sun. The type of nuclear power that is the most common on Earth is nuclear fission. Nuclear fission occurs when a heavier atom splits into smaller pieces. Usually the pieces are smaller atoms, but often neutrons are also released. Many fission reactions are initiated by a very heavy atom being hit, or in chemistry lingo, bombarded, by a neutron. This makes the already slightly unstable heavy atom even more unstable, which causes it to split into smaller atoms and possibly eject a few neutrons. This releases a lot of energy because the original atom was so unstable. Also, those neutrons that were ejected can be used to initiate several other fission reactions. This domino effect caused by the neutrons is called a chain reaction, and it can be responsible for keeping the reaction going for a long time. Whenever nuclear power is discussed, whether it be in the form of a nuclear reactor or a nuclear-powered submarine, the energy is produced because of a fission reaction. Another nuclear reaction we can take advantage of is the decay of carbon-14. Carbon is an essential element for living organisms that are constantly exchanging carbon, most of which is carbon-12. Some of those carbon atoms, though, are carbon-14 isotopes. While an organism is living, it has a set ratio of carbon-14 to carbon-12. After it dies, the stable carbon-12 remains while the radioactive carbon-14 undergoes beta decay to turn into nitrogen. Now, carbon-14 has a half-life of about 5,730 years. So every 5,730 years, half of it is going to decay into nitrogen. So the more carbon-14 that an artifact has, the more recent it is. Because many things were once living organisms or were once made from living organisms, measuring the percentage of carbon-14 in an artifact is a very reliable way of being able to tell how old the artifact is. Our next application of nuclear chemistry is in medicine. Sometimes, when diagnosing certain types of diseases, stable atoms in your body are replaced by radioactive atoms of the same element. These radioactive elements then move around throughout your body as they would normally. But because they're radioactive, they're easier to detect outside of the body. These are called radioactive tracers, and they act like little atom labels or flags. If they're being traced in locations where they shouldn't be, a more accurate diagnosis can be made. For example, technetium-99 is a common radioactive isotope that binds to many different molecules in the body. If it's combined with a tin compound, it is able to bind itself to blood cells, which can help create a map of your circulatory system. This may allow a physician to detect a disorder in your circulatory system. Another application of radioactive isotopes in medicine is in radiation therapy for the treatment of certain types of conditions. In some situations, a radioactive isotope is taken, which, depending on what type of molecule it is, will find its way to the appropriate spot in the body. It will then emit radiation that only travels a short distance, so it protects the surrounding tissues. The radiation that it emits could help kill any dangerous cells. These are just a few of the many examples of how big a role nuclear chemistry plays in our daily lives. From the fusion that occurs on the sun providing the energy for plants to grow, to the fission reactions that take place in nuclear power plants. Radioactive isotopes are measured to determine how old an artifact is, and they are administered in the body to detect and treat certain medical conditions. Simply put, our survival depends on nuclear reactions.
Places like Siberia and Antarctica are really, really cold, but they're no match for absolute zero. This is the lowest possible temperature. Absolute zero is a temperature of 0 Kelvin, or about -460 degrees Fahrenheit. This is so cold that scientists have not yet been able to reach this temperature, but they sure have gotten close. This is a state where the motion of particles comes to a near stop because there is so little energy left in the substance. Thankfully, we don't live in a world of absolute zero, which means that things are not that cold and that particles of objects have energy and are in motion. For some objects, like solids, this motion is more like vibration. This is why solid objects stay the same shape. Their particles like to hang out together in close proximity. Gases are quite different, though. Gaseous particles really like their personal space and are in a constant state of random motion. They fly around in random directions, filling the entire space of the container they occupy. This random motion doesn't mean that they fly around all willy-nilly, though. The particles fly in a straight line path until they collide with something else, either the boundary of the container or other gas particles that are also flying around randomly. When these collisions occur, they cause kinetic energy to be transferred, and this changes the particle's direction of motion. But gaseous particles are also traveling at random speeds as well as in random directions. Some particles move quite slowly, while others are traveling very fast, and the direction and speed of the particles is changing all the time. So it wouldn't make sense to measure all of the particles' velocities because there would be so much variation, and it would be difficult to pinpoint what one gas particle is doing at any given time. What we can do instead is look at a probability distribution of the speed of any given particle of gas in the container. Like any probability distribution, it tells us which situation is more likely to occur. This distribution is called the Maxwell-Boltzmann distribution, named for James Clerk Maxwell and Ludwig Boltzmann. If we pick any random gas particle from our container, it will fall somewhere on this curve, though it is more likely to be a certain speed than others. This is because as one particle collides with another, it will either gain kinetic energy, and therefore gain speed, from the particle it collided with, or lose kinetic energy to that particle, and therefore slow down. The distribution of speed stays the same because there is no change in the system, just a shuffling of change through the individual particles. It's like this. Say you're at a party where everyone carpooled to get there. You might have a total of 20 people at this party, and they all arrived in a total of 5 cars, but with different numbers of people in each car. So one car might have brought only one person, while other cars brought 2, 3, or even 5 people. At the end of the night, if everyone drives home with different people than they came with, you might have 5 people leaving in a car that originally brought only one person to the party, and 2 people leaving in a car that originally brought 4 people. The same number of people and cars are coming and going from the party, but each car has a different number of people. Now imagine that the people are kinetic energy and speed, and the cars are gas particles, and you can apply this same idea to gases in closed systems. When gas particles collide, some particles gain kinetic energy and speed, but others then have to lose energy and speed to keep the total energy of the system the same. The distribution of these speeds is represented under the curve of probabilities. What it shows us is that some speeds are more likely than others for any given particle because of this shuffling. Most particles fall within a certain range of speeds, but for that small number that have very high speeds, there are a similar number of particles traveling at very low speeds. In this way, they essentially balance each other out in the overall system. The shape of the Maxwell-Boltzmann distribution can change depending on a couple of factors. First, the average speed of the gas molecules is affected by temperature. Higher temperatures mean more kinetic energy, faster speeds, while lower temperatures mean less kinetic energy, slower speeds. So when the temperature of the system is increased, the curve flattens out and spreads over a wider area. It's like adding more cars to the carpool party. There are more ride options than before, so the distribution spreads out. But it also means that the probability of any one person getting in a specific car is less than before, so the curve flattens a bit too. The mass of the particles also plays a role in the shape of the curve. Just like an elephant moves more slowly than a mouse, molecules that are more massive also move more slowly than less massive molecules. So for a gas that has heavier particles, the curve will be much narrower because there is a narrower range of speeds possible for those particles. It will also be taller because there are fewer speed possibilities, which means those speeds are more likely. If there are suddenly fewer cars to drive people home from the party, your options are more limited than before, so the probability of you picking any one car that's left is greater than when you had more ride options. Gas particles are not fond of each other. In fact, they prefer to keep their space, and because temperatures on Earth are well above absolute zero, these particles are constantly flying around doing just that. Unfortunately for them, collisions do occur, and when this happens, the speed and direction of the particles involved in the collisions change. This makes it quite difficult to say exactly how fast and in what direction a particle is traveling at any given time. Instead, we can look to the Maxwell-Boltzmann distribution, which is a probability distribution of the speed of any given particle of gas in the system. The distribution tells us which speed is most probable for that particle. Because the probabilities change with temperature and molecular mass, the curves reflect this change by either flattening and spreading out or becoming narrower and taller. The flatter curve indicates that more speed options are possible for a given particle, but that the probability of having that speed is lower. In contrast, a narrower, taller curve indicates that fewer speeds are possible, but the ones that are possible are more likely for that particle.
One day during his vacation on Ideal Island, the place where all gases behave ideally, Johnny Dalton and his family decided to go for a walk through one of the villages on the island. While strolling down the sidewalk, Johnny's nose catches something amazing coming from one of the shops. The smell of delicious, fresh-baked chocolate chip cookies. This gets Johnny hungry and thinking. What was it that caused the smell of those chocolate chip cookies to drift out of the bakery and into his nose? The explanation to this aromatic question lies in the kinetic molecular theory, which describes the movement of ideal gas particles. It states that gas particles are constantly moving in random, rapid motion. So, if you have enough particles, or in this case cookie smell molecules, in one central location, they will eventually spread out because they are moving randomly and rapidly. The chemistry word for this phenomenon is diffusion, which is the movement of one substance through another. Usually it means particles will spread out or move from a region of high concentration to a region of low concentration. In my chocolate chip cookie example, the gas particles that contain the smells of the cookie are moving through the air from a high concentration, the bakery, to a low concentration, the sidewalk and surrounding area. After Johnny finishes the cookie he purchased, he continues on his walk. A while later, he notices something peculiar about his balloon. It appears to be sinking. What was once a high-flying helium balloon is now just a hovering and slightly smaller balloon. What do you think caused Johnny's balloon to lose some of its helium? Well, a phenomenon called effusion is to blame. Effusion is when gas particles exit through tiny holes in a container. Effusion occurs for the same reason as diffusion. Gas particles are moving in random, rapid motion. Because helium atoms are so small and light, helium is the lightest non-flammable gas, the particles can easily escape through the microscopic holes in the balloon, causing the balloon to get smaller and more dense, which makes it sink. In the mid-1800s, Thomas Graham experimented with effusion and discovered a very significant relationship. Lighter gas molecules will travel faster than heavier gas molecules. So, assuming the temperature and pressure remain constant, atoms or molecules with a lower molecular mass will effuse faster than atoms or molecules with a higher molecular mass. Graham even went further by finding out how much faster one molecule would be over another. This became known as Graham's law, and it states that the effusion rate of a gas is inversely proportional to the square root of its molecular mass. Usually this formula is used when comparing the rates of two different gases at equal temperatures and pressures. The ratio of the rate or speed of gas A over gas B is equal to the square root of the mass of gas B over the mass of gas A. So let's try using this equation with the following scenario. If oxygen molecules effuse at an average rate of 3 moles per second, how fast would hydrogen molecules effuse in the exact same conditions? Let's start out by filling in the information we know, and let's call hydrogen gas A and oxygen gas B. We know the rate of gas B is 3 moles per second, and the molecular mass of oxygen, a diatomic element, is 32 AMU. The molecular mass of hydrogen, also diatomic, is 2 AMU. My first step in solving this is to calculate the right side of the equation. 32 divided by 2 is 16. Notice how the units cancel out. The square root of 16 is 4. To solve for x, we would need to simply multiply both sides by 3 moles per second, which gives us an answer of 12 moles per second. So if oxygen is effusing at a rate of 3 moles per second, hydrogen would be effusing 4 times faster, at a rate of 12 moles per second. It is important to mention that the units on either side aren't important as long as they are the same. On the left side of the equation, you could use any rate units: moles per second, molecules per second, meters per second, miles per hour. And on the right side of the equation, any mass units could be used: AMU for molecular mass or grams per mole for molar mass. You just have to make sure the units on the top and the bottom of the fractions are the same. This formula works well for finding the rate of effusion in many situations, and it's a good approximation for comparing the rates of diffusion of two gases. For this last problem, we are going to compare the rates of ethanol, a common ingredient in perfume, C2H6O, and ammonia, NH3. If a bottle of each were opened at a distance away from you, which one would you smell first? We wouldn't need to set up the equation to answer this question. We would just need to determine which one is the lightest. But we are going to set up the equation just to get a little extra practice. So let's start out by assigning the ammonia as gas A and ethanol as gas B. Substituting the molecular masses of each into the right side of the equation gives us the square root of 46 divided by 17. If we calculate this, we get about 1.6. This means that ammonia will travel 1.6 times faster than the ethanol, and you will smell the ammonia before you smell the perfume. Gas particles are constantly moving in a random and rapid motion, which causes them to diffuse and effuse. Johnny was able to smell those chocolate chip cookies because of diffusion. The cookie smell became more spread out. The balloon Johnny was holding became smaller due to effusion. The helium in the balloon escaped through small holes in the walls of the balloon. Graham's law of effusion relates the rates of effusion with the mass of the substance. So when comparing two gases, the relative rates of effusion or diffusion are inversely proportional to the square roots of their masses.
Johnny Dalton has a very big day ahead of him. He is vacationing on Ideal Island, where all gases behave ideally. Johnny and his family are going to start off the morning by scuba diving around the island. As we follow Johnny during his dive, we'll be paying close attention to the role that gases play in this activity. More specifically, we will be seeing how Boyle's law helps us explain and predict some of the behaviors of gases. Johnny puts on his wetsuit and tank and jumps into the water. As he lowers himself under the surface of the water, he feels a little pressure in his ears. So he plugs his nose and blows out gently to equalize them. The reason he is feeling that pressure is because the surrounding water is pushing in on his ear. The deeper he gets, the more water pushes on his ears, which causes even more pressure to be put on his inner ear. As that pressure increases on the outside of his ear, the air inside the ear gets squished, and the volume inside decreases. The air doesn't go anywhere, it just gets squeezed together, which causes that uncomfortable feeling he had before to be equalized. When a scuba diver descends, he needs to equalize the pressure of the air inside the eustachian tube, the tube connecting the middle ear with the throat, with the pressure outside the eustachian tube. This is usually done by pinching your nostrils and trying to blow gently out your nose. If you try it right now, you may hear a little popping sound. That's the sound of your eustachian tube opening. We do this all the time by simply swallowing, although that's not a great idea underwater. Another thing Johnny notices as he descends is that his buoyancy compensator, which is just a vest filled with air, is getting smaller and smaller. Even his wetsuit is shrinking. What is causing this? Well, a scientist named Robert Boyle discovered that the pressure on a gas and its volume are inversely proportional to each other. This works for any closed system of gas, such as the inside of your ear, the buoyancy compensator, or even the thousands of tiny bubbles embedded in a neoprene wetsuit. If the temperature is held constant, the pressure of a gas increases as its volume decreases. The reverse is also true. As the pressure of a gas decreases, its volume increases. This is Boyle's law. Now, as Johnny was lowering himself under the water, all of those little containers of gas got smaller. The reason they did lies in the kinetic molecular theory, which we previously covered. One thing the kinetic molecular theory states is that gas particles are very far away from each other. This distance allows for the compression of gases. If the particles are far apart, they have room to move closer together. If the particles are already close together, like they would be in a liquid or solid, there's very little room for compression. Now, we also know that gas particles move randomly and rapidly, and each time they collide with the walls of their container, they apply a little bit of pressure. If we keep the same number of particles in a container, all with the same kinetic energy, but we decrease the size of the container, the particles will more frequently hit the walls of that container, causing the pressure to increase. Just like in Avogadro's law, this can be represented in the form of an equation. P sub 1 V sub 1 equals P sub 2 V sub 2. We use 1s and 2s to indicate the status before and after a change has taken place. Also, the units for pressure and volume don't matter, as long as they are the same for pressure and the same for volume. Let's say you have a 1-liter balloon at sea level, which is 1 atmosphere. If we were to release the balloon and allow it to float up to an altitude where it only experiences 0.5 atmospheres, what will happen to the volume? Well, we can think about it logically. If the pressure is decreasing by half, the volume will double. Or we can plug numbers into this equation. Our initial pressure is 1 atmosphere, and our initial volume is 1 liter. The final pressure is 0.5 atmospheres. So, if we solve for V sub 2, the final volume, this gives us 2 liters. Let's try another example. If Johnny's air-filled scuba vest holds 1.43 liters of air at 1.03 atmospheres of pressure, what volume of air will it hold at 10 meters underwater, which is equivalent to about 2.03 atmospheres? To solve this, we will start with our equation. The initial pressure times the initial volume equals the final pressure times the final volume. Our initial pressure is 1.03 atmospheres, and our initial volume is 1.43 liters. Our final pressure is 2.03 atmospheres, and our final volume is unknown. If we isolate V sub 2, we find that it is equal to 1.03 times 1.43 divided by 2.03, which is equal to 0.726 liters. That should make sense, because the pressure increased, so the volume should decrease. As Johnny is finishing his scuba diving adventure, he needs to make sure that he does not hold his breath as he ascends. If he doesn't let some air out of his lungs as he swims to the surface, he could damage his lungs. This is because there is less pressure pushing on his lungs as he moves toward the surface. As the pressure on his lungs decreases, the volume of the gas in his lungs increases, which can cause a dangerous situation. All of this applies Boyle's law, which states that as long as the temperature is held constant, the pressure and volume of a gas are inversely proportional to each other. Meaning, if one increases, the other one decreases. Often, the equation P sub 1 V sub 1 equals P sub 2 V sub 2 is used to make calculations involving Boyle's law. Johnny Dalton and his family have decided to take a hot air balloon ride over Ideal Island, the place where all gases behave ideally. Remember, ideal gases move rapidly and randomly. They don't lose energy when they collide, and there are no intermolecular forces among the particles. As his family is getting ready to embark on their hot air balloon ride, Johnny notices that the fuel for the balloon is just a simple torch. But how does a torch lift and move a hot air balloon? As you may recall, heating a gas will increase the speed of gas particles. After all, temperature is just a measure of the average kinetic energy of the particles. The higher the temperature of the particles, the faster the gas particles will be moving. According to the kinetic molecular theory, a concept we previously covered, faster gas particles are going to spread out. This causes the gas to take up more space. Well, what happens when fewer particles are taking up the same amount of space? To help you answer this, imagine you have 2 cubes filled with gas molecules. These cubes are the exact same size. The first cube has 5 molecules inside of it, and the second cube has 50 molecules inside of it. The one holding 50 will have more mass than the one holding 5. And though they are the same volume, their masses are different, so their densities will be different. When particles in a substance spread out and move farther away from each other, the substance becomes less dense. So, back to our hot air balloon. All the torch is really doing is heating the air inside the balloon, causing the air particles to move faster and spread out, which makes the balloon less dense than the air around it, which causes it to float. This phenomenon, hot air rising because of a decreased density, is also what causes it to be windy outside. The hot air that rises is replaced by cooler air. As the cooler air moves to replace the warmer air, you feel that movement as wind. In the late 1700s, Jacques Charles researched this relationship between the temperature of a gas and its volume. He discovered that if the pressure of a gas is held constant, as that gas is heated, its volume will increase. The reverse of that is also true. Cooling a gas will cause its volume to decrease. These relationships are known as Charles's law. This idea is what helped Lord Kelvin discover absolute zero. He measured the volume of several different gases at different temperatures, and he found the same relationship as Charles did. But this time, he wondered what would happen if he could cool something enough to make the volume equal to 0. He then extrapolated his data all the way down to a volume of 0, and the corresponding temperature at this volume was consistently around negative 273 degrees Celsius. This temperature became known as absolute zero. Just like the other gas laws, this one can be represented in the form of an equation. V1 over T1 equals V2 over T2. Remember, we use 1s and 2s to indicate the qualities before 1s and after 2s a change has taken place. Also, the units for volume don't matter, as long as they're both the same. The units for temperature must be Kelvin, K, or the equation will not work. Also, remember, this is a theoretical equation, because it only works for an ideal gas. Most gases that surround you and me behave very much like ideal gases, so we can use this equation as an approximation for the gases we encounter. Let's try a practice question. Say you have a 1-liter balloon filled with an ideal gas at room temperature, 293 Kelvin. If you were to put that balloon in your freezer, which has a temperature of 260 Kelvin, what would the new volume of the balloon be? We can start off by thinking about this problem logically. If the volume is decreasing, the molecules in the balloon are slowing down and getting closer together. This will cause the balloon to shrink. The temperature is only decreasing from 293 Kelvin to 260 Kelvin, so the volume will not decrease by much. We can plug the numbers into this equation and find out how much the balloon will shrink. The starting volume is 1 liter, and the starting temperature is 293 Kelvin. The final temperature is 260 Kelvin. If we solve for T2, we get 0.887 liters as a final volume. You can solve for V2 a couple of different ways. I solved by cross-multiplying the 1 and 260, and then dividing by 293. You could also rewrite the equation as an equality. V1 times T2 equals T1 times V2. So 1 liter times 260 Kelvin will equal V2 times 293. Solving for V2 will give us 0.887 liters. Let's try a trickier example. This time, your temperature will be given in Celsius, and you must first convert to Kelvin. This technique was covered in a previous lesson. Say you have a 500 milliliter unopened bag of potato chips at room temperature, 20 degrees Celsius. Now, you take this bag of potato chips outside on a hot summer day when the temperature is 38 degrees Celsius. What is the final volume of the bag of potato chips? As I mentioned, to solve this, you will need to use Kelvin as a temperature unit. So, to convert degrees Celsius to Kelvin, you must add 273. This makes our room temperature 20 plus 273 equals 293 Kelvin. It makes our outside temperature 38 plus 273 equals 311 Kelvin. I think we're ready to start using the equation. Our initial volume is 500 milliliters, and our initial temperature is 293 Kelvin. Our final temperature is 311 Kelvin. Solving for V2 gives us 531 milliliters. This makes sense because as the gas warmed up, the particles sped up and got farther apart, which caused the container to expand. Near the end of the hot air balloon ride, the torch heating the air in the balloon is used less frequently. As the air in the hot air balloon cools, the particles slow down and move closer together. When the particles move closer together, the air becomes more dense, causing the hot air balloon to sink. This is one of several situations where you can see Charles's law at work. Charles's law states that the volume of a gas is directly proportional to the temperature of a gas. Often, the equation V1 over V2 equals V2 over T2 is used to make calculations involving Charles's law.
Johnny Dalton is enjoying his day at the beach on Ideal Island, the place where all gases behave ideally. So what makes them behave so ideally? Ideal gas particles move rapidly and randomly, they don't lose energy when they collide, and they do not have any intermolecular forces. This means that when two ideal gas particles get near each other, they are not attracted to each other, like real gas particles may be. As he lays his towel out and gets his sunblock out, he notices a warning on the back of the aerosol can. Contents under pressure. Do not heat. Why would heating this aerosol can be a cause for warning? Johnny thinks for a minute and then recalls some of the ideas of kinetic molecular theory. He remembers that as the temperature of a gas increases, the gas particles move faster and faster. After all, temperature is really just a measure of the average kinetic energy of the particles. Also, when gas particles are moving quickly, they hit the insides of their container more frequently. Finally, because pressure is just a measure of the force of the particles hitting the inside of the container, the more times it hits the inside of the container, the higher the pressure will be. Now, the container that is holding these particles may not be able to withstand those high amounts of pressure. If the pressure inside of the container exceeds the limits of the container, an explosion could occur. If you live in cold climates, you may notice that the pressure in your car's tires decreases as it gets colder. This is because the air particles inside the tires are colder and moving slower. They don't hit the inside walls of the tires as frequently, and the pressure in your car's tires decreases. This relationship between temperature and pressure is known as Gay-Lussac's law. It states that if the volume of a container is held constant, as the temperature of a gas increases, the pressure inside the container will also increase. As with the other gas laws, this one can be represented in the form of an equation. P1 over T1 equals P2 over T2. Now recall that we use 1s and 2s to indicate the quantities before, with the 1s, and after a change has taken place, with the 2s. Also note that the units for pressure do not matter, as long as they're the same throughout the entire equation. The units for temperature must be kelvins, or the equation will not work. This is because the Kelvin scale is an absolute scale. It doesn't go negative. Finally, this equation only works for an ideal gas. Most gases that surround you and me behave very much like ideal gases, so we can use this equation as an approximation for the gases we encounter. Let's say you are making dinner using a pressure cooker with an initial internal pressure of 1 atmosphere and an internal temperature of 100 degrees Celsius, or 373 kelvins. Assuming the volume does not change and the gas behaves ideally, what will the pressure inside the container be if the temperature is raised to 200 degrees Celsius, or 473 kelvins? To solve this, you will need to make sure you are using the Kelvin temperatures. Substitute the numbers into the correct locations in the equation given to us. So 1 atmosphere over 373 kelvins equals P2, which is our new pressure, over 473 kelvins. Solving for the final pressure can be done by cross-multiplying and dividing. This gives us a final pressure of 1.27 atmospheres. Let's try a more complicated example. If a container of an ideal gas has an initial pressure of 300 torr and the temperature is 25 degrees Celsius, if the pressure in the container is increased to 1 atmosphere, what temperature change caused this increase in pressure? Well, before we start to solve this problem, we must first convert one of the pressure units so they're both the same. I'm going to convert atmospheres into torrs, but you could easily convert torrs into atmospheres. I know that each atmosphere of pressure is equal to 760 torr, so I'm going to substitute in 760 torr for my 1 atmosphere. Before I can solve this equation, I also need to convert 25 degrees Celsius to kelvins. This can be done by adding 273 to the temperature in Celsius. This gives me 298 kelvins. When I plug all of these numbers into the formula, I get 300 torr over 298 kelvins equals 760 torr over T2. I'm going to solve for T2 by cross-multiplying the 298 kelvins and the 760 torr. I will then divide by the 300 torr to give me a final temperature of 755 kelvins. This should make sense because the final pressure was a bit more than double the initial pressure, which would mean that the final temperature should be a bit more than double the initial temperature. Every day, you are surrounded by gases that behave in a very predictable manner. As the temperature of a gas increases, the particles move faster. If a container can expand, it will. If a container cannot expand, this increase in particle speed will result in an increase in pressure inside the container. This pressure and temperature relationship is an example of Gay-Lussac's law. It is the reason pressure cookers are able to cook food really fast. And it's the reason Johnny will make sure to keep the sunblock aerosol can away from the fire. Gay-Lussac's law can also be represented in equation form as P1 over T1 equals P2 over T2. Using the equation helps out a great deal when solving numerical problems.
Cities, states, and countries all have different laws. This is because what works for some places doesn't work for others. You wouldn't want the speed limit in the middle of a busy city to be the same as it is on the highway because that doesn't make sense. Scientific laws are different though. We call them laws because they have been studied and experimented through and through, helping us understand, predict, and explain natural phenomena like gravity. Every once in a while though, just like speed limits, these laws only make sense under certain circumstances, which we call ideal conditions. When this happens, we can adjust the law ever so slightly so that it helps us understand the phenomena under not so ideal conditions. We find this to be true with gases. As we learned in another lesson, the ideal gas law, which is the scientific law that describes gas behavior, is written as PV equals nRT. In this equation, P is the pressure of the gas, V is the volume of the container holding the gas, N is the number of moles of gas, R is the ideal gas constant, the same for all gases, and T is the temperature of the gas. Most of the time, this law is just what we need to understand the behavior of a gas. We call gases that can be described by the ideal gas law ideal gases. Under ideal conditions, we can use this equation to find the pressure, volume, number of moles, or temperature of a gas as long as we know the other missing variables. However, a gas may act differently under not so ideal conditions, such as really high pressures and densities or at very low temperatures. These gases that exhibit different properties under extreme conditions are known as real gases. And in order to describe this behavior, we need to deviate slightly from the ideal gas law and use a modified version of the equation. Luckily for us, the work here has already been done. Dutch scientist Johannes van der Waals realized that there was a problem with two of the assumptions that are inherent to the ideal gas equation. The first assumption is that the molecules of a gas make up a negligible amount of the total volume of that gas. The second assumption is that the attraction between the molecules of a gas is also negligible. Let's start with the first assumption. Under normal circumstances, we can roll with this assumption and use the ideal gas equation to describe gas behavior. But as a gas is compressed, the total volume inside the container becomes less. The molecules of the gas also become more significant in terms of the amount of space they're taking up relative to the overall space of that container. Think of it this way. All of the cars in the US are currently spread out over the entire country, so each individual car only takes up a negligible amount of space relative to the total space available. But if you were to put all of the cars in the US into the state of Rhode Island, the space they take up suddenly becomes quite significant compared to the overall available space. The volume of each car can no longer be neglected, and the same is true for gas molecules. Compressing a gas also forces us to re-examine the second assumption. This is because gas molecules are, in fact, attracted to each other, especially when they're close together. It's like having a large room full of people who don't know each other. At first they are nervous, so maybe only one or two people talk to each other in the center of the room. But if you were to make the room smaller so that all of the people were forced closer to each other, more conversations start and people are less likely to spread to opposite sides of the room to avoid each other. The same is true for gas molecules. As a gas is compressed, the molecules are forced closer to each other and they become more attracted to each other. This also means that there is less pressure on the container because the molecules are huddling together in the middle instead of flying around hitting the walls. So what can we do to adjust the ideal gas law for real gases? We again look to our two assumptions about gas molecules. First, since molecules do have volume, we need to deduct this from the total volume of the container. So instead of just V, we adjust the variable so that we have V minus NB. Here, N is the number of molecules in moles, since this is proportional to the volume they take up, and B is a constant that is different for each gas, equal to the volume 1 mole of particles from that gas occupies. So with this first adjustment, the equation now looks like this. P times V minus NB equals nRT. But we're not done yet. We still have to adjust for the attraction between the molecules. To do this, we add another term to the pressure in the equation, which looks kind of messy, but really isn't that bad. The new term is A times N squared divided by V squared. V is still the volume, and N is still the number of moles of gas. A is just another experimentally derived constant, N is different for each gas, just like B, relating to the degree of attraction between the molecules. Once we put all of this together, our finished equation looks like this. P plus A times N squared divided by V squared times V minus NB equals nRT. Not so bad, right? We call this the van der Waals equation in honor of all the hard work he did for us. One question you may be asking yourself is why the two constants, A and B, are different for each gas. Well, different gases have different size molecules, so the constant B relates to the different volumes these molecules will have. The degree of attraction A is also different because some molecules are more attracted to each other than others, so we need a specific number for each gas. Using the ideal gas law is often a perfectly fine way to solve for the pressure, temperature, volume, or number of moles for a given gas. Under ideal conditions, this equation works because we can assume that the attractive forces of the gas molecules, as well as the volume of those molecules, are negligible. However, under extreme conditions, like very high pressures or very low temperatures, we need to let go of these assumptions and account for the volume and attraction of the gas molecules. This is because these two factors become more important under extreme conditions. Just like taking all of the cars in the US and putting them into one city, or smushing a group of partygoers into a smaller room. All of a sudden there is less space overall, so the relative volume and attractive forces of the molecules have a greater effect. Dutch scientist Johannes van der Waals realized that there was a problem with the two assumptions that go along with the ideal gas equation. Using what we now call the van der Waals equation and known gas constants, we can easily solve for any of the same variables we would using the ideal gas law. The difference is that thanks to him, we can also understand gas behavior in less than ideal conditions. In another lesson, we learned how real gas behavior deviates from ideal gas behavior under non-ideal conditions. They behave differently because these non-ideal conditions are pretty stressful, very high pressures and densities, and very low temperatures. In order to account for this change, we need to modify the ideal gas law slightly. These changes include constants that quantify the volume of the gas molecules as well as the attractive forces between those molecules, both of which are considered negligible under ideal conditions. Originally, the ideal gas law looks like this. PV equals nRT. P is the pressure in atmospheres, V is the volume of the container in liters, N is the number of moles of gas, R is the ideal gas constant, 0.0821 liter atmosphere per mole Kelvin, and T is the temperature in Kelvin. For real gases, we make two changes by adding a constant to the pressure term P and subtracting a different constant from the volume term V. The new equation looks like this. P plus AN squared over V squared times V minus NB equals nRT. Here, A is the constant for the attraction between the molecules of a given gas, think A for attraction, and B is the volume those molecules take up inside the container. You may have noticed a few extra n's tagging along with those two constants, and that is because A and B are values for 1 mole of that gas. So we have to multiply the constants by the total number of moles to get the correct value. And remember, the constants are different for each gas since each gas has different properties. This new equation is called the van der Waals equation in honor of Dutch scientist Johannes van der Waals, who did a lot of hard work to figure out how real gases behave. Though this equation looks different than the ideal gas law, you can still solve it in the same way as long as you know the other variables. The difference here is that you also need to know the values for the constants A and B, which, luckily for us, are available and can easily be looked up. To see how real gases behave, let's start with a simple example using the ideal gas law. Say we have the gas CO2. We have 1.00 moles N at 273 Kelvin T, and it's in a container with a volume of 22.4 liters V. To solve for the pressure P, we simply rearrange the equation and do the math. What we find is that P equals nRT over V, or equals 1.00 moles times 0.0821 liter atmospheres per mole Kelvin times 273 Kelvin, all divided by 22.4 liters, and we get 1.00 atmospheres. Now let's find the pressure using the van der Waals equation. Remember, everything is the same except we now have to incorporate A and B. For CO2, A equals 3.640 liters squared atmospheres per mole squared, and B equals 0.04267 liters per mole. Here's how it looks now. What we find now is that P equals 0.995 atmospheres. That's pretty close to our first answer, so what's going on here? Well, at normal temperatures and pressures, we will get essentially the same result using either the ideal gas law or the van der Waals equation. So what we need to do is put this gas to the test under some pretty extreme conditions. Let's try it again, but this time let's change the volume of the container so that it is much smaller, say 0.100 liters. We expect the pressure to increase because there's less space for the gas to take up, meaning the molecules will bump into the container's walls more often. Using the ideal gas law, we find that P equals 1.00 moles times 0.0821 liter atmospheres per mole Kelvin times 273 Kelvin divided by 0.100 liters equals 224 atmospheres. That's a lot of pressure. Now let's see how this deviates when we use the van der Waals equation for real gas behavior. If we plug in our variables, we get our pressure now is only 31.5 atmospheres. Do you see how P is very different than if we use the ideal gas law? It's still a greater pressure than under the ideal conditions, but why is it so much lower than our result obtained from the ideal gas equation? This is because when using the van der Waals equation, we take into account the strong forces of attraction between the CO2 molecules. As the molecules are forced into a tighter space, they do in fact bump into the container walls more often, but they also stay closer together because the attractive forces increase as they are squished into a tighter space. Using the ideal gas law, we can find the pressure, volume, temperature, or number of moles of an ideal gas. But for real gases, we need to use the van der Waals equation because it factors in the relative effects of the volume of the gas molecules as well as the attraction between those molecules. However, once we insert these constants into the equation, the process of solving for the missing variable is the same. The van der Waals equation is written like this: P plus AN squared over V squared times V minus NB equals nRT. It looks very similar to the ideal gas law, PV equals nRT, except now we account for the attraction between the gas molecules with A and the volume of those molecules with B. N gets used a few more times too because the volume and attraction are values for only 1 mole of that specific gas. So we simply multiply each constant that we look up by the total number of moles of gas to get the correct amount.
The idea of pH was proposed in 1909 by a Danish chemist named Søren Sørensen to solve an annoying problem chemists were having. Chemists had found that when they were working with acids and the concentration of hydronium ions, H3O+, the numbers in the calculations involved negative exponents. Sørensen proposed using the negative logarithm of H3O+ to measure acidity. Sørensen called the new measurement pH. The P stands for power and the H for hydrogen, so pH stands for power of hydrogen. pH is just a value used to express how acidic or basic solution is. The pH scale runs from 0, the lowest possible value, to 14, the highest possible value. Values from 0 to 6 are acidic, a value of 7 is neutral, and values from 8 to 14 are basic. Here's a fun pH experiment you can do at home. Red cabbage is a natural pH indicator. Mix chopped cabbage with boiling water and allow the mixture to sit for 10 minutes to leach out the flavin, a pigment. After 10 minutes, pour out just the water. It should be a purple color. When the solution is purple, the pH is neutral. Divide the solution into different containers and start adding various household liquids to the containers. If the solution turns red, the solution you added was acidic. If it turns yellow-green, then the solution you added was basic. To calculate the power of pH, the formula is negative log times the concentration of H3O+. Although this sounds complicated, it really isn't. If you have a hydronium ion concentration, H3O+, of 1 times 10 to the negative 7th, the pH is 7. Negative log concentration H3O+ equals negative log times 1 times 10 to the negative 7th equals 7. If the concentration of H3O+ is 1 times 10 to the negative 1, the pH is 1. If it is 1 times 10 to the negative 13, the pH is 13. See how that works? The following problem is a bit harder because you are given the molarity of the solution and not the concentrations of the ions. What is the pH of a 0.00010 molar solution of HNO3, a strong acid? Because the problem told you that HNO3 is a strong acid, you know that it dissociates nearly 100%. So you know that the H3O+ concentration equals 1 times 10 to the negative 4th molar. 0.0001 equals 1 times 10 to the negative 4th. pH equals negative log concentration H3O+ equals negative log times 1 times 10 to the negative 4th equals a negative 4 equals 4. Here's another one. You'll need a calculator for this one. Calculate the pH of a 0.2 molar solution of a strong acid. Strong acid, therefore H3O+ concentration is the same as the molarity of the solution, or concentration H3O+ equals 2 times 10 to the negative 1. pH equals negative log times concentration H3O+ equals negative log times 2 times 10 to the negative 1 equals 0.7. What is the pH of a 0.0136 molar solution of KOH, a strong base? This one is a bit harder because you have the hydroxide ion concentration, but not the hydronium ion concentration. Because you were told that the KOH is a strong base, you know it dissociates nearly 100% to form 1.36 times 10 to the negative 2 OH concentration. If you remember that the Kw, or auto-ionization constant of water, is calculated by the formula concentration H3O+ times the concentration OH- equals Kw equals 1 times 10 to the negative 14th, you can figure out the H3O+ concentration. H3O+ concentration equals Kw divided by the OH- concentration. H3O+ concentration equals 1 times 10 to the negative 14th divided by 1.36 times 10 to the negative 2. H3O plus concentration equals 7.35 times 10 to the negative 13th. Now that you know H3O plus concentration, you can figure out the pH. pH equals negative log H3O plus concentration equals negative log times 7.35 times 10 to the negative 13th. pH equals 12.13. Try another one. Calculate the pH if the OH minus concentration equals 2 times 10 to the negative 3 molar. First, figure out the H3O plus concentration from the formula H3O plus concentration equals Kw over OH minus concentration. H3O plus concentration equals 1 times 10 to the negative 14th divided by 2 times 10 to the negative 3rd equals 5 times 10 to the negative 12. Now that you know the H3O plus concentration, you can figure out the pH. pH equals negative log concentration H3O plus equals negative log times 5 times 10 to the negative 12 equals 11.3. You can use the pH of a substance to calculate the concentrations of the hydronium ions and hydroxide ions. What are the concentrations of hydronium and hydroxide ions in acid rain that has a pH of 5.05? Known values. pH equals 5.05. Kw equals 1 times 10 to the negative 14th. Concentration H3O plus equals question mark. Concentration OH minus equals question mark. Find the H3O plus concentration from the equation concentration H3O plus equals 10 to the negative pH. Concentration H3O plus equals 10 to the negative 5.05. H3O plus concentration equals 8.9 times 10 to the negative 6 molar. Use the auto-ionization equation to find OH minus concentration. Concentration H3O plus times concentration OH minus equals Kw equals 1 times 10 to the negative 14th. Concentration OH minus equals Kw divided by concentration H3O plus. Concentration OH minus equals 1 times 10 to the negative 14th divided by 8.9 times 10 to the negative 6th. Concentration OH minus equals 1.1 times 10 to the negative 9 molar. What is the hydronium ion and hydroxide ion concentration in juice that has a pH of 3.3? Known values. pH equals 3.3. Kw equals 1 times 10 to the negative 14th. Concentration H3O plus equals question mark. Concentration OH minus equals question mark. Find the concentration H3O plus from the equation concentration H3O plus equals 10 to the negative pH. Concentration H3O plus equals 10 to the negative 3.3. Concentration H3O plus equals 5 times 10 to the negative 4th. Use the auto-ionization equation to find concentration OH minus. Concentration H3O plus times concentration OH minus equals Kw equals 1 times 10 to the negative 14th. Concentration OH minus equals Kw divided by concentration H3O plus. Concentration OH minus equals 1 times 10 to the negative 14th divided by 5 times 10 to the negative 4th. Concentration OH minus equals 2 times 10 to the negative 11th. pH is a value used to express the acidity or alkalinity, basicity, of a solution. It is measured on a scale of 0 to 14, with 0 to 6 being acidic, 8 to 14 being basic, and a value of 7 representing neutral. You can calculate the pH of an acid or base solution given the hydronium ion concentration by using the formula pH equals negative log concentration H3O plus, or if given the hydroxide ion concentration by the formula concentration H3O plus equals Kw divided by concentration OH minus. Then using the pH equals negative log concentration H3O plus formula. You can also use the pH of a substance to calculate the concentrations of the hydronium and hydroxide ions by using the formula concentration H3O plus equals 10 to the negative pH.
At least 60% of the average human is made of water. A lot of that water can be found in our blood, and our blood is 83% water. It's really important for our blood to have a pH of about 7.4, which is slightly basic, because otherwise we get really sick. You might recall that an acid is a hydrogen ion donor and raises the hydrogen ion concentration in a solution while decreasing the pH of that solution. And a strong acid is a hydrogen donor or acid that completely dissociates in water. For example, hydrogen chloride dissociates from HCl bonded together into a hydrogen ion and a chloride ion. On the other hand, a base is a hydrogen ion acceptor. It lowers the hydrogen ion concentration in a solution while increasing the pH of that solution. And a strong base is a hydrogen ion acceptor that can completely dissociate in water. Now we know that water has a pH of 7, which means that its concentration of hydrogen ions in solution is 1 × 10⁻⁷ moles per liter. So this tells us that some dissociation of water is going on. The pH of blood is about 7.4, and it needs to remain there so that we don't become ill. Given that most of our blood is water, something must be going on to maintain the pH of our blood around 7.4. Now it turns out that the reason our blood can maintain this pH and keep us from getting sick is weak acids and weak bases. Now these are really important because if all acids and bases were strong acids and bases, they would all completely dissociate when they got into water, and they would all just keep reacting with each other. Us humans would be one giant walking exothermic acid-base reaction, and that wouldn't be good for anyone. An important acid in blood is carbonic acid, H2CO3. Carbonic acid can dissociate in water to give hydrogen ions and hydrogen carbonate, HCO3-. In this case, carbonic acid is serving as an acid to give away hydrogen ions and leaving a conjugate base, which is made by removing a hydrogen ion from a particular acid. Similarly, hydrogen carbonate, acting as a base, can react with hydrogen ion to form carbonic acid, which is the conjugate acid, which is formed by adding hydrogen ion to a base. Now, not all weak acids are exactly the same. Some weak acids are stronger than others, and there is a way that we can measure this, which is called the acidity constant. For a particular reaction where we have an acid, in this case I'm going to call it HA, so H is the hydrogen ion that it's going to give away, it can dissociate partially to give some A- and some hydrogen ion as its products. To figure out how far this reaction's gone, we can take the concentration of hydrogen ion, multiply it by the concentration of A-, and divide that by the concentration of HA that's still left in the solution. This gives us the Ka. Now if we look at the dissociation of carbonic acid, we find that its Ka is equal to the concentration of hydrogen ions times the concentration of hydrogen carbonate in solution divided by the amount of carbonic acid that is still in the solution. At room temperature, we find that this is 7.9 times 10⁻⁷. Now these numbers are not very pleasant to look at. So similarly to pH, we modify this and we have something called the pKa, which is the negative log of the Ka. So in this case, the pKa of carbonic acid is 6.1, which is on the stronger end of things. Carbonic acid is considerably more acidic than water is, which is no surprise given that water gives us a neutral pH. Now carbonic acid is an important component of blood and helps to regulate its pH. And you might wonder why it would be there since it has a pKa of 6.1 and seems to want to give away a lot of hydrogen ions. It turns out that carbonic acid is part of what we call a buffer system. And this is actually something that's really cool about weak acids and bases, is that we can put a weak acid and its conjugate base in a solution to create a solution whose pH will not change when small amounts of acid or base are added. Now blood, which needs to have a pH of around 7.4 with an acceptable range of 7.35 to 7.45, has 3 buffer systems to help keep it in check. The first one is this carbonate buffer system that we already talked about. In blood, carbonic acid is primarily responsible for removing acid from the environment. So the conjugate base, hydrogen carbonate, is incredibly important. It reacts with hydrogen ions that are formed in our bodies, for example, when we exercise. It removes these hydrogen ions, reacting with them to form carbonic acid. This carbonic acid can then travel around in our blood to the lungs, where it can dissociate into water and carbon dioxide. And then the carbon dioxide can be released through our lungs into the atmosphere. This is an important part of respiration and helps to maintain the pH of our blood. In addition to carbonate as a buffer system in blood, proteins can act as buffers because they can accept and donate hydrogen ions. The other important buffer system in our blood is the phosphate buffer system. The phosphate buffer is really good at dissociating when base is added to the system to help increase the hydrogen ion concentration, to help maintain the pH of blood at about 7.4. And the pKa of dihydrogen phosphate is about 7.1. Having these three buffer systems in our blood is incredibly important because they can work together to keep the pH of our blood stable. Buffers are really important in biology, in our bodies, and also in the lab. In the lab, scientists use buffers in their biological experiments to help create for cells and proteins the environments that they find where they naturally would come from. To recap, we've learned that acids give away hydrogen ions and that they can be strong acids that completely dissociate in water or weak acids that partially dissociate. We've learned that bases are substances that can accept hydrogen ions. These bases can be strong bases, which completely dissociate, or weak bases, which only partially dissociate. We've learned that the conjugate acid of a base is the molecule that is formed when that base has accepted a hydrogen ion. We've also learned that the conjugate base of an acid is the molecule that is formed when that acid has given away a hydrogen ion. We've learned that blood contains three important buffering systems, and we've learned that the acidity constant and pKa can tell us about how strong or weak an acid is. A lower pKa is a stronger acid.
What do a bag of cement, acid rain, and the synthesis of aspirin have in common? I know, tricky question so early in the lesson. Well, the answer is they all involve important chemical molecules called anhydrides. The term anhydride means without water. Anhydrides are able to react with water to produce either an acid or a base. Before we look at anhydrides in more detail, I want to quickly remind you of what we mean by an acid and a base. The simplest definition of an acid is a substance that releases hydrogen ions, H+, in water. And the simplest definition of a base is a substance that releases hydroxide ions, OH-, in water. These simple definitions work well for us here. We can recognize an acid molecule because it has hydrogen ions to give away. And we can recognize a base because it has hydroxide ions to give away. Anhydrides can thus be divided into two main types, and we will look at each one in turn. Acid anhydrides are molecules that form acidic solutions in water. An acid anhydride are the oxides of non-metals that can react with water. In solution, they form molecular acids. Now, it is important to realize that not all non-metal oxides are acid anhydrides, only those that can react with water. For example, carbon monoxide is an oxide of carbon, but does not react with water. Therefore, it is not an acid anhydride. Here we have two common and important reactions. The first is the formation of sulfuric acid. Here, sulfur trioxide gas reacts with water to form sulfuric acid. You can recognize sulfuric acid because it has two hydrogens to give away. This reaction is important because it is a producer of acid rain. Acid rain is formed from pollution. In particular, acid rain is usually formed from pollution from coal plants that produce sulfur dioxide, SO2.
Once in the air, sulfur dioxide reacts with oxygen to form sulfur trioxide. This is the acid anhydride in our reaction. Once it is formed, it quickly reacts with water vapor in the atmosphere and falls as acid rain. Acid rain has devastating effects on the environment. So for this reason, regulations have been introduced to reduce the amount of sulfur dioxide in the atmosphere from industry. These regulations have successfully decreased the amount of acid rain. Another important acid anhydride reaction is the formation of carbonic acid. This time carbon dioxide is reacting with water to form carbonic acid. Again, you can recognize it as an acid because it has hydrogens to give away. Carbonic acid is also involved in the formation of acid rain, but it is even more important in its role in changing the pH levels of our oceans, rivers and streams. From our reaction, I'm sure you can see that the more carbon dioxide there is in the atmosphere, the more carbonic acid will be produced. This is of real concern to scientists as the oceans become more acidic because of increased levels of atmospheric carbon dioxide. Acid anhydrides are also extensively used in organic chemistry. They are used in the manufacture of all sorts of things, including industrial chemicals, pharmaceuticals, perfumes and explosives. And if you have a bad headache, you may take aspirin. So an important reaction for many people is the use of acid anhydride in the synthesis of aspirin. Let us now move on to base anhydrides. These are molecules that form basic solutions in water. Base anhydrides are the oxides of group 1 and group 2 metals. They react with water to form the hydroxide ion as one of the products. A typical base anhydride reaction is the reaction of calcium oxide. Here, calcium oxide reacts with water to form calcium hydroxide. You can recognize calcium hydroxide as a base because of the hydroxide ions it can give away. This is the exact reaction that takes place when water is added to dry cement. Calcium oxide or quicklime is an ingredient in cement. For this reason, it is really important to protect your skin when you are working with cement or grout for tiling. Continued contact of your hands with these products can lead to irritation. This is because calcium hydroxide further reacts with the water in your skin, breaking down into calcium and hydroxide ions. The hydroxide ions are very caustic. In this lesson you have learned that the term anhydride means without water. Acid anhydrides are non-metal oxides that can react with water to form acidic solutions. Important acid anhydride reactions include the reaction of water vapor with sulfur trioxide and carbon dioxide. Base anhydrides are group 1 and 2 metal oxides that can react with water to form basic solutions. An important use for base anhydrides is in the production of cement.
Electrochemistry. This is where the chemical world meets the electrical world. Electrochemistry is when chemical energy is transformed into electrical energy, which is then often transformed into another kind of energy, such as light or heat. It is extremely important to us because of how much electricity we use in our daily lives. Electricity, remember, is the flow of electrons through a path, usually a wire. The whole path is called a circuit. A flashlight is an example of electrochemistry. Its batteries are undergoing a chemical reaction that transfers chemical energy to electrical energy to light energy. The flashlight battery is an electrochemical cell. An electrochemical cell is something that changes chemical energy to electrical energy. It contains 2 compartments, each with an electrode submerged in an electrolyte. The electrode is just a conductor, usually a metal that connects to a non-metallic part of a circuit. The electrolyte is a fluid that conducts electricity. One of the plates is positive and one of them is negative. Those 2 plates are called the cathode and anode, and they're connected by a wire that completes the circuit. Often one metal strip in the battery is copper, and it acts as a cathode, which is the electrode where reduction takes place and electrons are gained. The other electrode is the anode, often zinc, where oxidation takes place and electrons are lost. Electrons leave the system from the anode and go into the wire. So what happens is the electrons on the anode are lost and travel through the wire to the cathode, where electrons are gained. The solutions the two electrodes are in helps conduct the electrons from the surface of the electrode to the wire. The two electrodes are in separate compartments, separated by a porous barrier or salt bridge. The barrier or bridge allows the ions in both solutions to move from one side to the other, to prevent charge from building up on the electrodes. The chemical reaction that occurs in the electrochemical cell is a redox or reduction-oxidation reaction. As its name implies, that reaction is made up of two parts, a reduction reaction where electrons are gained, and an oxidation reaction where electrons are lost. Here you see a two-compartment container filled with an electrolyte solution. On this left side, there is a zinc piece for the electrode. This electrode is the anode because it loses electrons. On the right side is a copper piece for the electrode. This electrode is a cathode because it accepts electrons. Connect the anode to a light bulb with a copper wire. Then connect the light bulb to the cathode with the wire. The circuit is now complete, and the electrons flow from the anode into the light bulb, where it turns into light energy. Then the electrons go back down the wire into the cathode. You can make your own battery at home with a lemon, copper pennies, and galvanized nails, a wire, and an LED light. Put the penny in one side of the lemon and the nail in the other side of the lemon. Make sure they don't touch. The nail and the penny are the electrodes, with the nail being negative and the penny being positive. The lemon juice is the electrolyte. Use a wire to connect the nail to an LED and then to the penny. The LED should light up because the circuit is complete. If your LED does not light up, it may be that your penny isn't pure enough copper or the lemon battery isn't strong enough. You can connect lemons in series by connecting one to another with wire to boost the voltage of your battery. An electrochemical cell is something that changes chemical energy to electrical energy. It consists of two electrodes submerged in an electrolyte that are connected by a wire. The positive electrode is called the cathode and accepts the electrons. The negative electrode is the anode and donates the electrons. The chemical reaction is usually an oxidation-reduction reaction that involves the transfer of electrons from a substance that gets oxidized to a substance that gets reduced. Batteries. They're useful things. Whether it is for your TV remote or your flashlight, it stinks when they lose power. In this lesson, you'll learn how batteries work and why they die. You previously learned that an electrochemical cell consists of two half cells, an anode and a cathode. The anode is the electrode where oxidation occurs and electrons are lost. The cathode is where reduction takes place and electrons are gained. These reactions don't occur separately. They must work together in a reduction-oxidation reaction. For this next section, let's assume the electrodes are zinc and copper. There are other metals that can act as electrodes, but let's keep it simple and stick with these two. The half reaction on the anode where oxidation occurs is Zn solid equals Zn2 plus aqueous plus 2 electrons. The zinc loses 2 electrons to form Zn2 plus. The half reaction on the cathode where reduction occurs is Cu2 plus aqueous plus 2 electrons equals Cu solid. Here the copper ions gain electrons and become solid copper. The entire reaction can be written by combining both half reactions. Zn solid plus Cu2 plus aqueous equals Zn2 plus aqueous plus Cu solid. This equation for an electrochemical cell may also be shown as anode electrode, anode solution, cathode electrode, which would then look like Zn solid, Zn2 plus aqueous, Cu2 plus aqueous, Cu solid. So although both reactions happen at the same time, they are separated by a barrier, so the only place for the electrons to move is through the wire connecting the anode and cathode. This is how you capture the electricity that is being produced. Another type of electrochemical cell is a zinc-carbon dry cell. This is your size C and D batteries. These batteries have a zinc container that is the anode that is filled with a paste of MnO2, graphite, and NH4Cl. They have a carbon rod going down their middle, which is the cathode. When the circuit is closed, like when it is in a flashlight and the flashlight is turned on, the half reaction on the anode is Zn solid equals Zn2 plus aqueous plus 2 electrons. The reduction half reaction on the cathode is 2MnO2 solid plus H2O liquid plus 2 electrons equals Mn2O3 solid plus 2OH minus aqueous. The electrochemical cells you have learned about are voltaic cells. A voltaic cell is one in which a spontaneous redox reaction produces electricity. In a voltaic cell, as you know, the oxidation reaction at the anode pulls electrons into the wire that connects the cathode to the anode. It is called electric potential, and it is measured in volts. More specifically, electrode potential is the potential difference between an electrode and its solution, or the amount of pull on the electrons. It is the amount of energy needed to move an electric charge across a cell. The two half cells of the battery each have potential to either give up electrons or take electrons. The difference between the two is the electrode potential of the whole cell, or voltage. Fortunately, the electrode potential isn't something you need to memorize. Scientists have determined standard electrode potentials for many different types of electrodes. To determine the voltage of any cell, look on a table of electrode potentials. Subtract the electrode potential of the anode from that of the cathode, and you get the electrode potential of the cell, or voltage. EO cell equals EO cathode minus EO anode. This number is easy to calculate. For example, calculate the voltage of a cell for the reaction of liquid mercury electrode in a solution of mercury 1 nitrate and a cadmium metal electrode in a solution of cadmium nitrate. If the EO isn't provided to you, you can refer to a chart for the value. Electrode reaction, EO volts. CD2 plus, CD2 plus. The formula for the half reactions are Hg2, 2 plus aqueous, plus 2 electrons equals 2 Hg liquid, which has an EO equal to 0.850 volts. Cd2 plus aqueous plus 2 electrons equals Cd solid, which has an EO equal to negative 0.403 volts. EO cell equals EO cathode minus EO anode. EO cell equals 0.850 volts minus negative 0.403 volts. Remember that two negatives make a positive. EO cell equals 1.253 volts. Try another one. Zn2 plus aqueous plus 2 electrons equals Zn solid, which has an EO equal to negative 0.762 volts. 2 H2O liquid plus 2 electrons equals H2 gas plus 2 OH minus aqueous, which has an EO equal to a negative 0.828 volts. EO cell equals negative 0.762 volts minus a negative 0.828 volts. EO cell equals 0.066 volts. As you know, the Alaskan pipeline is a long steel pipe that brings oil from Alaska to the lower 48 states. What would happen if it corroded? Would oil spill all over our environment? How do we protect metal from corrosion? Corrosion is when metal is gradually destroyed through chemical reactions. Because it is a chemical reaction, we can prevent it with chemical reactions, namely redox reactions. One of the metals that is most affected by corrosion is iron. When iron is corroded, rust is formed in the reaction 4Fe solid plus 3O2 gas plus H2O liquid equals 2 Fe2O3 H2O solid. The amount of rust that forms depends on the amount of water available for the iron to react with. The two electrochemical half reactions are Fe solid equals Fe2 plus aqueous plus 2 electrons. This is the anode. O2 gas plus 2 H2O liquid plus 4 electrons equals 4 OH minus aqueous. This is the cathode. The anode and cathode are both on the same piece of iron, but different regions of it. You know that for this reaction to work, the electrons need a wire of some sort, or some way of conducting the electron flow. In this case, the iron itself acts as the wire. So when an iron piece gets exposed to oxygen and water, a site on the iron is oxidized and loses electrons. These electrons flow through the iron to another site where they are reduced. Here they form a solid called hydrated iron oxide, 2Fe2O3H2O solid. The water layer on the surface of the iron acts as a barrier or salt bridge that is needed for the electrochemical cell or reaction to work. The way to prevent corrosion is to have a different metal present that is more easily oxidized than the metal you want to protect. Zinc is more easily oxidized than iron, so if you coat the iron with zinc, the zinc will corrode before the iron does. This protects the iron. This is called cathodic protection because you are adding a protective cathode to the metal. Nails are an example. Iron nails are often coated in zinc in a process called galvanization to protect them from rusting. The Alaskan pipeline is another great example of this type of protection. Instead of coating the whole thing in zinc, the pipeline is connected to zinc wires. The zinc will corrode before the steel, and as long as the corroded zinc gets replaced periodically, the pipe itself will not corrode. This is a great thing. Electrochemical cell reactions consist of two half reactions, one on the anode electrode and one on the cathode electrode. The two half reactions can be added together to make the full cell reaction. Electrode cell potential is measured in volts. It is easy enough to figure out the voltage of any electrochemical cell if you have a table that lists the voltage for each type of electrode. To determine the voltage of any cell, subtract the electrode potential of the anode from that of the cathode, and you get the electrode potential of the cell, or voltage. EO cell equals EO cathode minus EO anode. Corrosion is when metal is gradually destroyed through chemical reactions, and it is a real problem in our daily lives. Since corrosion is a chemical reaction, we can prevent it with chemical reactions, namely redox reactions. The way to prevent corrosion is to have a different metal present that is more easily oxidized than the metal you want to protect. As in most things in life, chemical reactions take the path of least resistance and least energy, so the metal that is easier to oxidize will be corroded, and the other metal will be protected.
Scientist 1. Hey, do you know the concentration of this strong acid solution X? Scientist 2. No, but I know how we can figure it out. Scientist 1. How? Scientist 2. By strategically mixing it with a strong base. Scientist 1. How could that possibly tell us anything useful about the concentration of X? Performing a reaction could change the properties of the substance. Scientist 2. Don't worry, my friend. Pay attention and I will tell you. Let's think about the reactions between strong acids and strong bases. These reactions are often referred to as neutralization reactions. Any guesses why? Well, when you add strong acids to strong bases, the hydrogen ions from the acid react with the hydroxide ions from the base to create a neutral product, water. Acids and bases react in a 1-to-1 ratio. When you add base to acid, or vice versa, once the pH is neutral, 7, you know that you have equal parts acid and base present. If you keep track of how much solution you've added to reach neutral pH, you can determine the concentration of the unknown. This process is called titration. Titration is when a solution of known properties, called the titrant, is used to analyze properties of an unknown solution. Titrations are often used in acid-base chemistry to determine the concentration of an unknown solution. In a titration like the one proposed by our cartoon scientists, we take a sample of our strong acid of unknown concentration. We then add some strong base, just a little at a time, until the concentration of the hydrogen ions equals the concentration of hydroxide ions. This point, known as the equivalence point, is when the amount of hydrogen ions and hydroxide ions are equal and the pH equals 7. We find this point either by monitoring the pH with a probe or adding indicator solution, a special chemical that changes colors within a specific pH range. Ideally, the equivalence point occurs when titration stops. The point at which titration stops is called the end point. Since we know how much titrant we added, we can infer the concentration of the unknown solution. We'll look at this more in depth later. Data collected during titration can be used to create a titration curve, or a graph of pH versus volume of titrant added. Titration curves start with the pH of the unknown solution and end with the pH of the titrant. All titration curves have similar characteristics. To me, they all look like slides. Like many slides, titration curves begin with a slope that is gentle and gradual initially, dramatic in the middle, then gentle at the end. The equivalence point occurs in the middle of the dramatic slope. A titration in which a strong acid is titrated using a strong base will have a titration curve that looks like graph 1. A slide modeled after this curve would certainly be an intense, if not scary ride. Initially, the pH of the solution is low, changing very gradually until suddenly there is a sharp increase in pH. As previously noted, the equivalence point is located in the middle of this slope. For strong acid, strong base titrations, the equivalence point is 7. If titration continues beyond the endpoint, pH values continue to rise to that of the pure base. Can you picture what a titration curve would look like when a strong base is titrated with a strong acid? It should be the opposite of the titration curve we just looked at. Initially, the pH is high, changing very gradually until there is a sudden, sharp decrease in pH. As titration continues, pH decrease becomes more gradual. The way you determine the concentration of the unknown substance from the titration data is to use the equation concentration of hydrogen ions times the volume of hydrogen ions equals the concentration of hydroxide ions times the volume of hydroxide ions. Make sure concentration is in terms of molarity, or moles per liter, and volume is in terms of liters. Step 1. Gather the information. You need to know the concentration and volume of acid or base that you added and the amount of the unknown substance you started with. Step 2. Set up your equation and fill in all the known values. Step 3. Do the calculations. Here's an example. A 40 milliliter hydrochloric acid solution, HCl, is titrated with 24.64 milliliters of a 0.55 molar potassium hydroxide, KOH, solution. What is the concentration of the HCl solution? Step 1. Gather the information. The volume of the hydrogen ions is 40 milliliters. We convert that to liters by dividing by 1,000. Volume of hydrogen ions then becomes 0.04 liters. The concentration of hydroxide ions is 0.55 moles per liter. The volume of hydroxide ions is 24.64 milliliters, which equals 0.02464 liters. The concentration of hydrogen ions is a mystery. Step 2. Set up the equation and fill in the known values. Here's our equation again. We can rearrange to solve for concentration of hydrogen ions by dividing both sides by the volume of hydrogen ions. Now we plug in our values. The concentration of hydrogen ions equals 0.55 moles per liter times 0.02464 liters divided by 0.040 liters. Step 3. Do the calculations. Liters will cancel out. So, concentration of hydrogen ions will equal 0.55 moles per liter times 0.02464 liters divided by 0.040 liters. Concentration of hydrogen ions equals 0.3388 moles per liter. So, the concentration of the hydrochloric acid solution is 0.3388 moles per liter. Titrations between strong acids and bases will always result in a pH of 7 at equivalence point. How cool is that? This phenomenon occurs because strong acids and strong bases dissociate 100% in solution. Also, the conjugate acids and bases produced by strong acids and strong bases do not affect pH. If you need to determine the pH during titration at points other than the initial or end point / equivalence point, then you will need to do some math. Determining the pH at any given point of a titration for a strong acid and strong base is easy. To determine pH, we'll need the concentration and volume of the substance being titrated, and we'll need the concentration and volume of the titrant added at the interval of interest. We'll do a little stoichiometry to figure out the pH. Our process is best summarized, though, in 3 easy steps. Step 1, determine the moles of each reactant present. Step 2, determine which reactant is in excess. And Step 3, calculate pH based on the concentration of the excess reactant. Imagine we are titrating a 10 milliliter sample of 2 molar hydrochloric acid with 0.5 molar potassium hydroxide and want to know the pH after we have added 20 milliliters of potassium hydroxide. We know that hydrochloric acid and potassium hydroxide react in a 1-to-1 ratio to produce water and potassium chloride, KCl. Neither of these products influence pH, so we don't have to consider their presence in our stoichiometric calculations. Step 1. Determine the number of moles of each reactant present. 100% of the hydrogen ions have come from the hydrochloric acid, so we need to determine the number of moles of hydrochloric acid in solution. To do this, we multiply molarity of hydrochloric acid by volume of hydrochloric acid in liters. 2 molar hydrochloric acid times 0.010 liters equals 0.020 moles of hydrochloric acid, or 0.020 moles of hydrogen ions. Next, we determine the number of moles of hydroxide ions that have been added. Similarly, 100% of the hydroxide ions in solution have come from the potassium hydroxide. We multiply the molarity of potassium hydroxide by the volume that has been added. 0.5 molar potassium hydroxide times 0.020 liters equals 0.010 moles potassium hydroxide. This is the same as 0.010 moles hydroxide ions. Step 2. Determine which reactant is in excess. We have 0.020 moles hydrogen ions and 0.010 moles hydroxide ions. These species react in a 1-to-1 ratio, which will leave us with leftover hydrogen ions. Assuming 100% of the hydroxide ions react with the hydrogen ions, 0.010 moles of hydrogen ions will remain. Step 3. Calculate pH based on the concentration of excess reagent. Since we know the number of moles of hydrogen ions that will remain in solution, we can divide by the total volume of the solution to determine the concentration of hydrogen ions. And then we can determine the pH. So we take 0.10 moles hydrogen ions, divide by 0.010 liters plus 0.02 liters. This equals 0.33 molar hydrogen ions. pH equals the negative log of the concentration of hydrogen ions. The negative log of 0.33 equals 0.48. That's our pH. Titration is when a solution of known properties, called the titrant, is used to analyze properties of an unknown solution. Titrations are often used in acid-base chemistry to determine the concentration of an unknown solution. Neutralization reactions occur when hydrogen ions from strong acids and hydroxide ions from strong bases react to make water. The equivalence point of a titration occurs when equal amounts of hydrogen ions and hydroxide ions are in solution. For strong acids and strong bases, pH at the equivalence point is 7. Titration curve, or a graph of pH versus milliliters of titrant added, can be made from data from titration. Titration curves for strong acids and strong bases have dramatic slopes. To determine concentration of an unknown using titration data, use the equation concentration of hydrogen ions times volume of hydrogen ions equals concentration of hydroxide ions times volume of hydroxide ions. Make sure concentration is in terms of molarity, or moles per liter, and volume is in terms of liters. To determine pH during titration at any other point other than equivalence point, follow these 3 steps. Step 1. Determine the moles of each reactant present. Step 2. Determine which reactant is in excess. Step 3. Calculate pH based on the concentration of the excess reactant.
Have you ever taken an antacid like Tums or Rolaids to quell the effects of a spicy or acidic meal? The antacids are bases that react with the acids in your stomach to produce a neutral product that will help decrease the burning sensation in your stomach. The type of chemical reaction that occurs is called a neutralization reaction. Chemists use neutralization reactions to analyze acidic or basic solutions in a technique called titration. During titration, a solution of known properties, called the titrant, is used to analyze properties of an unknown solution. Titrations may be done to determine the initial concentration of the unknown solution, or to measure changes in pH as the titration occurs. Imagine that you have to take 3 antacid tablets to neutralize the acid in your stomach. The point at which neutralization occurs is called the equivalence point. This is best described chemically as the point at which equal amounts of acid and base have been added together to create a neutral solution. The equivalence point is the most important point of a titration because it gives us information about how much unknown is present. Ideally, the equivalence point is the same as the endpoint, or stopping point of a titration. Unfortunately, we can't just feel the endpoint of a titration like we can when we're taking antacids. Instead, we either need to use an indicator solution or do some math to predict the pH at equivalence point. An indicator solution is a special chemical solution that changes color within specific pH ranges. If we know what kinds of acids or bases we're titrating, we can choose a specific indicator to help us find our endpoint. If we know the identity of the acids and bases we're titrating and their concentrations, we can do math to predict the pH at equivalence point. Data collected during titration can be used to create a titration curve, or a graph of pH versus milliliters of titrant added. All titration curves have similar characteristics to me. They all kind of look like slides. Like many slides, titration curves begin with a slope that is gentle and gradual initially, dramatic in the middle, and then gentle at the end. The equivalence point occurs in the middle of the dramatic slope. A titration in which a weak acid is titrated with a strong base will look like this. A slide modeled from this curve would be a more mellow ride. Starting pH values are lower, ending pH values are higher, the slopes of the lines are not as dramatic, and the equivalence point is higher than 7. A titration in which a weak base is titrated with a strong acid will look very similar to the previous titration curve, except backwards. The starting pH will be relatively high, and the ending pH will be relatively low, but not as extreme as if this was a titration between a strong base and a strong acid. The slopes of the lines aren't as steep, and the equivalence point occurs below 7. Notice that when an acid is titrated with a base, the pH increases from left to right. When a base is titrated with an acid, the pH decreases from left to right. If a weak acid or base is present in titration, the slopes will always be more mellow than if both substances are strong acids and bases. If you want to learn more about strong acid-base titrations, please check out our video. Determining the pH of a weak acid or base that is titrated by a strong acid or base is kind of a labor-intensive process. If you've watched the video on titrations with strong acids or strong bases, you are already familiar with most of this process. To determine the pH in a titration that involves a weak acid or weak base, we will determine the number of moles of each reactant present, determine which reactant is in excess, then use stoichiometry and Ka values, or Kb values, to determine hydrogen ion concentration and pH. We'll break this step into 3 smaller steps later. Imagine we're titrating a sample of acetic acid, HC2H3O2, Ka value 1.8 times 10 to the negative 5th, with NaOH as our titrant. Our acetic acid sample is 1.5 molar and 50 milliliter. Our NaOH has a concentration of 1 molar. We want to know what our pH will be after 5 milliliters of titrant has been added. Acetic acid reacts with NaOH in a 1-to-1 ratio to produce water and sodium acetate. The acetate ion is a relatively strong conjugate base and affects pH. Step 1. Determine the number of moles of each reactant present. The initial number of moles for our reactants can be found by multiplying molarity by volume. For simplicity's sake, I'll refer to the compound HC2H3O2 as acetic acid. 1.5 molar acetic acid times 0.050 liters acetic acid equals 0.075 moles of acetic acid. 1 molar NaOH times 0.005 liters NaOH equals 0.0050 moles NaOH. To simplify, I'm just going to call NaOH OH negative. Step 2. Determine which reactant is in excess. We have significantly less OH negative than acetic acid, so pH will be based on the amount of acetic acid remaining. Like in the previous problem, the base added will react completely with the weak acid. This will leave us with no OH negative and 0.070 moles of acetic acid. 0.075 moles acetic acid minus 0.005 moles acetic acid reacting with the OH negative equals 0.070 moles remaining. Now things are going to get a little complicated. We have determined the amount of acetic acid in solution and identified that species is the major contributor to pH. But acetic acid is a weak acid, so it only dissociates a tiny bit. Plus, the reaction between acetic acid and NaOH produced the acetate ion, which affects pH. To tackle the third step, we will use an ICE table to help us organize our calculations and concepts. An ICE table stands for initial concentration, change in concentration, and equilibrium concentration. It looks like this. I often augment my ICE tables with an additional row on top where I write my reactants and products. It helps me keep track of what chemical species are involved. The goal of an ICE table is to figure out the equilibrium concentration of a species after it has undergone a change. In this case, the change is the dissociation of acetic acid. The species we're interested in is the hydrogen ion. Step 3 can be broken into 3 parts. 3A, filling in the ICE table. 3B, writing the equilibrium expression for the dissociation of the acid. And 3C, plugging in the equilibrium concentrations determined in the ICE table into the equilibrium expression and solving for the concentration of hydrogen ions. The expression for the dissociation of acetic acid is HC2H3O2 breaking down into H plus C2H3O2 minus. I put all this information into the top row of my ICE table. I know from step 2 that I have 0.070 moles of acetic acid. I also know that the initial reaction between NaOH and acetic acid produced some of the acetate ion. Because NaOH and acetic acid react in a 1-to-1 ratio, the amount of acetate ion produced should be equal to the amount of OH that reacted, 0.0050 moles. ICE tables express amounts of chemicals in terms of concentration. To find concentration, I divide moles by total volume, 0.055 liters. Initially, we have no hydrogen ions, but not for long. The dissociation of acetic acid will produce hydrogen ions. The amount produced is contingent upon the dissociation constant and the presence of the acetate ion. The presence of the acetate ion will discourage acetic acid from dissociating as much. To fill in the next row, we'll let the number of hydrogen ions produced from the dissociation of acetic acid equal X. Since dissociation happens in a 1-to-1 ratio, the number of hydrogen and acetate ions produced will both equal the number of acetic acid particles. The amount of acetic acid will decrease by X, while the amount of both hydrogen ions and acetate ions will increase by X. Now that we have the equilibrium concentrations, we can solve for X by putting these values in the equilibrium expression for the dissociation of a weak acid. If you don't recall how to do this, please watch the video on Ka and Kb values. We know that Ka for acetic acid is 1.8 times 10 to the negative 5, and that the equilibrium expression is Ka equals concentration of hydrogen ions times concentration of acetate ions divided by the concentration of acetic acid. If we plug in all the information about the equilibrium conditions, we have 1.8 times 10 to the negative 5th equals X times 0.005 moles divided by 0.055 liters plus X divided by 0.070 moles divided by 0.055 liters minus X. Yuck. Look at how many times X occurs in this expression. Solving for X could take forever. Instead, let's make a few assumptions about the value of X. The Ka value of X is really small, meaning that the fraction of acetic acid particles that actually dissociate is likely to be very small. This number is so small that it's safe to ignore the impact it will have on our initial concentrations of both acetic acid and acetate. We will solve this equation for only the x representing hydrogen ion concentration. 1.8 times 10 to the negative fifth equals x times 0.005 moles divided by 0.055 liters divided by 0.070 moles divided by 0.055 liters. That looks way better. According to this operation, x equals 2.5 times 10 to the negative fourth molar. This was an okay move because the value of x was less than 5% of the initial acetic acid concentration. The rule for approximations like these is known as the 5% rule. Now we can input this into our pH expression. pH equals negative log 2.5 times 10 to the negative fourth. This equals 3.6. What a doozy. But we did it. Titrations are used in acid-base chemistry to analyze properties of an unknown solution. In a titration, a titrant, a solution with known properties, is added to a solution of unknown properties. The equivalence point is the point at which equal amounts of acid and base have been added together to create a neutral solution. The endpoint is the stopping point of a titration. Ideally, the endpoint of a titration is the equivalence point. A titration curve is a graph that shows how pH changes as titrant is added to the unknown solution. Titrations all look similar. Initial pH changes gradually, then abruptly, then gradually again. Titrations between weak acids and strong bases or strong acids and weak bases produce less dramatic titration curves. Titrations between weak acids and strong bases have equivalence points that are above 7. Titrations between strong acids and weak bases have equivalence points below 7. When determining pH during a titration that involves a weak base or a weak acid, follow these 5 steps. Step 1. Determine the moles of each reactant present. Step 2. Determine which reactant is in excess. Step 3a. Filling in the ice table. Step 3b. Writing the equilibrium expression for the dissociation of the acid. Step 3. Plugging in the equilibrium concentrations determined in the ice table into the equilibrium expression and solving for the concentration of hydrogen ions.
Laws govern much of our everyday lives. Traffic laws demand that you stop at a stop sign. Tax laws tell you that you must give a portion of your salary to the state and federal government. The law of gravity predicts a poor outcome for someone attempting to fly. The laws of thermodynamics are scientific laws that directly affect our lives. The first law, energy is neither created nor destroyed. The first law of thermodynamics states that energy can be converted from one form to another, but energy can neither be created nor destroyed. It is sometimes referred to as the law of conservation of energy. Let's consider the energy powering your computer right now. Where did it come from? The first law of thermodynamics tells us that it could not be created out of thin air. Therefore, let's try to trace it to its source. The computer is powered by electricity, which comes from a power plant. The power plant could produce this electricity in any number of ways, but let's say it's a hydroelectric plant associated with a dam. The water stopped by the dam has accumulated potential energy. This potential energy can be released by allowing the water to flow through the dam, and in the process move a turbine, which will in turn cause a generator to produce electricity. Water collected at the dam because the dam blocks a large river. The water flowing in the river is moving until it reaches the dam, thus it has kinetic energy. Therefore, in this example, your computer is being powered by the kinetic energy of the river, which is transformed into potential energy stored by the dam, which is converted back into kinetic energy as it flows through the turbine and finally is transformed into electricity by the generator. The second law, not all energy can be used. However, we know that energy is eventually lost over time. If you give your stalled car a push, the car doesn't continue to move indefinitely. Instead, it slowly comes to a stop. This seems to defy the law of conservation of energy, right? The second law of thermodynamics states that not all energy can be used. In the case of the car, pushing the tire across the pavement infused kinetic energy into the car. However, As the rubber scrapes against the pavement, heat is generated due to friction. Heat is a form of energy. Although the car appears to be losing energy, the total energy in the system has not changed. The energy has been transformed into unusable energy in the form of heat. We can say that the usable energy in the system has been lost to entropy or disorder. Therefore, another way of stating the second law is that entropy or disorder tends to increase over time. Taken together, the total energy of the system is equal to the usable energy, called free energy, plus the unusable energy. Thus, if a series of energy transformations occur in a closed system, a portion of the free energy is lost at every step as entropy increases. The first law of thermodynamics states that energy can be converted from one form to another, but energy can neither be created nor destroyed. The second law of thermodynamics states that not all energy can be used, and disorder tends to increase.
Imagine that you want to climb Mount Snowdon in my home country of Wales. Wales is the little country just left of England. You can get up to the top of the mountain two different ways. You can spend 2 to 4 hours hiking to the 3,560 feet peak, or you can take the train, which is a nice leisurely 1-hour ride to the top. Because you can't hike up in a straight line, your hiking distance is much more than the height of the mountain. The train, on the other hand, has a much more direct route to the peak. Both ways will get you to the top, and in both cases your altitude from start to finish will change by 3,560 feet. Critically, it didn't matter how you got to the top of the mountain, the change in altitude was the same. This is an example of a state function, which is a property whose value does not depend on the path taken to reach that specific value. In other words, it didn't matter whether you climbed the mountain by foot or went by train, you still ended up 3,560 feet higher up than when you started. Your final position in both cases was the same. Now, not everything is a state function. Let us explore the way you got up the mountain. If you hiked up, you put in a lot more effort to do the climb. But if you took the train, you put in very little effort to get up the mountain, as the train was doing all the work for you. So the amount of effort put in by you was different and depended on which way you went up the mountain. We call this effort work. Work is a path function and not a state function, because the value changes depending on the pathway you take. The ultimate question in figuring out whether something is a state function is, do I care how I got the final value? If the answer is no, then it is a state function. Now you are probably sitting there thinking, why on earth do I care? Why would I ever need to know about state functions? Mathematicians care a lot about state functions and spend a lot of time writing equations about them. But fortunately for us, we don't really need to understand the math. We just need to know how we can use state functions. We come across state functions a lot in thermochemistry and thermodynamics. Many of the equations involved in these topics include properties that are state functions. What is really cool about state functions is that they make calculations simple and easy. All we need to know is the state change, the change in value between the final and starting position. We do not need to know how this change happened. State functions really help us with something called Hess's law. We won't go into that in detail here, since Hess's law is covered in another lesson. Okay, so now that we've reviewed what state functions are and why they are used, let's explore some properties that are state functions. We'll start with temperature. Let's say we have a glass of room temperature water measuring 22 degrees Celsius. So what would happen if I add a large ice cube? The temperature will go down, of course. With the ice cube, our water drops from 22 degrees Celsius to 18 degrees Celsius. So time for some harder questions. Would the final temperature be any different if the big cube was broken into 3 smaller ice cubes? Would it be any different if the 3 smaller ice cubes were added one at a time at 10-second intervals? The answer to both questions is no. As long as the final temperature is the same for each glass, and in our case it is 18 degrees Celsius, it doesn't matter how the cooling was done. Temperature is a state function. Two other really important properties in chemistry that you will frequently come across are energy and enthalpy. Both energy and enthalpy are state functions. These concepts lie at the heart of thermochemistry and thermodynamics. There are many other properties that fall into the state function category. The most important ones to know for chemistry are mass, pressure, density, energy, temperature, volume, enthalpy, entropy, Gibbs free energy, and chemical composition. Each one relies only on change in the final and initial state and not on how we got there. So just like our climb up the mountain, all that mattered was the change in altitude and not that we took the train or chose to hike. To help you remember the important properties that are state functions, learn this phrase. Many people deserve entertaining television. Everyone enjoys great comedies. In this lesson, you learned that a state function is a property whose value does not depend on the path taken to reach that specific value. In other words, it does not matter how you get there. All that is important is where you started and where you finished. State functions are really important in thermochemistry and thermodynamics. State functions help us simplify our calculations and see the change in value between the final and starting position, also known as state change. Mass, pressure, density, energy, temperature, volume, enthalpy, entropy, Gibbs free energy, and chemical composition are all examples of state functions in thermochemistry. Let us consider two common processes, a plant photosynthesizing and a candle burning. Both are chemical reactions, and so there is a change of reactants into products. Both processes also involve a change in energy. A change in energy accompanies every chemical reaction. Enthalpy change is the measure of energy change during a chemical reaction. So let us look at each process and see if we can see what is going on. First, the burning candle. The wax is reacting with oxygen, forming a flame and producing carbon dioxide and water. If you put your hand close to the flame, you will burn yourself because it is hot. The flame is giving off heat. On the other hand, the plant is just sitting there absorbing the UV rays from the sun. This time the heat is coming from the sun and going into the leaf. So can you tell what is different about these two processes in terms of energy or heat? Don't worry if you can't quite explain it. By the end of this lesson you will be able to. This lesson is all about heat and energy transfer during chemical reactions. Energy is at the center of everything we do, but it is actually really difficult to precisely define it. I will simply define energy as the ability to do work or produce heat. An important type of energy is potential energy. Potential energy is energy due to position or composition. Potential energy is present in the chemical bonds of molecules. One of the most important characteristics of energy is that it is conserved. The law of conservation of energy states that energy can neither be created nor destroyed. It is converted from one form to another. This law is also known as the first law of thermodynamics. If we return to the candle and the plant, we can illustrate this. For the candle, the potential energy contained in the candle wax and the oxygen is released. It is then transferred into the potential energy of the products. The extra energy left over is transferred out as heat. For the plant, the energy from both the sun's UV rays and carbon dioxide are transferred into the products, which are oxygen and glucose. This time, though, there is no excess energy. In fact, there is a deficit in energy, so heat from the sun is absorbed by the plant to make up this deficit. Heat transfers into the plant. For both reactions, energy is transferred from one form to another. Let us now consider two very important concepts that often get confused: heat and temperature. Temperature is a measure of the random motion of particles. We can easily measure temperature by using a thermometer. The air around the candle flame is a much higher temperature than further away. Heat is the transfer of energy between two objects due to temperature difference. It is important to know that the transfer of heat is always from hot to cold, and never the other way around. In both reactions, heat is either being transferred in or transferred out. Now we are going to consider the direction of heat transfer during a chemical reaction. To really focus in on a specific chemical reaction, we have to divide the universe into two. The system is the part of the universe we are interested in. The surroundings include everything else in the universe. For a candle burning, the reactants and products is the system. The surroundings are the air in the room and anything else. When a reaction results in heat being given out, it is called exothermic. Energy in the form of heat flows out of the system. The candle is burning and energy flows out of the system as heat. Reactions that absorb heat energy from surroundings are called endothermic. Heat flows into the system. Our plant is a great example of an endothermic process. It is absorbing heat from the sun. It is important to realize that the transfer of heat into or out of the system equals the amount of heat lost or gained in the surroundings. Energy must be conserved. So far, we have learned that a change in energy accompanies every chemical reaction. We have also seen that reactions can give out heat or take in heat. But how do we measure change in energy of a reaction? This is where enthalpy change comes in. With our new knowledge, you can think of enthalpy change as the amount of heat absorbed or released by a chemical reaction. Let's look at the enthalpy changes for our two examples. When a candle burns, the potential energy from the reactants has been transferred to the products. Here you can see the potential energy of the system has gone down. The extra energy left over from the reaction is transferred to the surroundings as heat. Remember, the heat gained by the surroundings must be equal to the heat lost by the system. We can measure the temperature change of the surroundings, and we can directly relate this to the enthalpy change of a system. In an exothermic reaction, the potential energy of the products is lower than the reactants. Heat has been transferred to the surroundings, and the temperature of the surroundings goes up. For our plant photosynthesizing, again the potential energy from the reactants has been transferred to the products. But this time the products are at a higher energy. Extra energy is transferred into the system by the plant absorbing heat energy from the sun. Again, we can measure the heat of the surroundings and directly relate it to the enthalpy change of the system. In an endothermic reaction, the potential energy of the products is higher than the reactants. Heat has been transferred from the surroundings and the temperature of the surroundings goes down. You will notice on each diagram we have a symbol delta H. This is the change in enthalpy. It is very easy to figure out the amount of enthalpy change of a reaction. You can use this simple equation. All you have to do is add up all the enthalpies of the products and then subtract all of the enthalpies of the reactants. The difference between the two is the enthalpy change. If the difference ends up with a negative number, then you have an exothermic reaction. If the difference ends up as a positive number, then you have an endothermic reaction. And make sure you don't lose the positive sign so you are clear which type of reaction you have. In this lesson, you have learned that enthalpy is the energy transferred during a chemical reaction. The law of conservation of energy tells us that energy is neither created nor destroyed, it is transferred from one form to another. Temperature and heat are not the same. Temperature is a measure of the random motion of particles in the system, and heat is the transfer of energy due to a temperature difference. In an exothermic reaction, the potential energy of the system goes down and heat is given out. In an endothermic reaction, the potential energy of the system goes up and heat is taken in. The enthalpy change of a reaction is the difference between the sum of enthalpies of products and the sum of enthalpies of reactants, and the amount of heat exchanged with the surroundings can be directly related to the enthalpy change of the reaction.
Hello, my name is Callie Carbon, and I'm here to tell you all about me, because I am super important. I know what you're thinking. Callie Carbon kinda sounds self-absorbed, but I really am important. In fact, there's an entire branch of chemistry dedicated just to me called organic chemistry, or the study of carbon-containing molecules and the compounds they form. Before we go on, people often think of organic as natural or pesticide-free, but in chemistry it doesn't mean that. So go ahead and enjoy your organic tomatoes, but realize that has a different meaning than the organic in chemistry. Anyways, not all substances that contain carbon fall into the organic chemistry category. For example, a diamond is made up of carbon atoms, but studying diamonds wouldn't make you an organic chemist. So I should add, organic chemistry usually involves the study of molecules that have the carbon-hydrogen bond, but you'll see various definitions depending on where you're looking. Yeah, hydrogen and I are pretty close, and we usually hang out together. And we can be found in everything that is or was alive. So that includes you, your dog Rex, and even your houseplant. But there's more. We can be found in the gasoline in your car, your plastic water bottle, and even the asphalt on the highway. Before we talk about why I'm so important, let's take a closer look at what organic chemists study. They look at the structure and composition of carbon-containing molecules. Some molecules are small, some are large, some have double bonds, and others have rings. There are many different organic molecules, so there are many different structures. Some are made of just carbon and hydrogen, whereas others have other elements too. Organic chemists look at the properties of organic compounds. For example, are they a solid at room temperature, or are they a gas? Do they dissolve easily in water? They examine how organic molecules can be prepared. For example, what happens if you combine 2 or 3 organic molecules? What type of new compound do you get? Finally, they look at the different reactions that can occur. So you might be wondering, why is carbon the element that's so important? Why not neon or chlorine? I don't want to put down my fellow elements. I mean, neon and chlorine are friends of mine. But they can't do what I can do. For starters, I can bond or attach with 4 other elements at the same time. This is because I have 4 valence electrons, or the outermost electrons farthest from the center or nucleus of an atom. In order to reach stability, atoms like to have 8 valence electrons, so I tend to share 4 other electrons with another atom, which gives me 8 total. So I bond or attach to other atoms through covalent bonds, or the bond formed when atoms share electrons. Each valence electron is involved in bonding, so this is why I can attach or bond to 4 other atoms at once. But that's not all. In addition to bonding with 4 different atoms at once, I'm also pretty special because of the way I can bond. For example, I can form simple bonds and make something like methane, attaching to 4 hydrogen atoms. Or I can make a more complicated molecule by bonding with other carbons and forming a chain. I can make a branching chain. I can double back and make rings. And I can even form double or triple bonds with other atoms. I'm sure talented. So you probably get the idea that I can bond with many different elements in many different ways, and so I can make millions of different organic molecules or molecules that contain carbon. Many of these organic molecules are important to you, even if you don't know it. Not only do I make up 18% of your body, but I'm also the building blocks for tons of stuff inside of you. I make up the sugar that gives you energy, the protein that makes your muscles, the enzymes that help the chemical reactions occur faster in your body, the DNA inside of your cells, the fats that cushion your organs. Okay, I know. I can't stop talking about myself. Since I am the element that makes up so many important parts of the human body, you can start calling yourself a carbon-based life form. Without carbon, there wouldn't be life on Earth. So yeah, I am a pretty big deal. But other than making up your body, your water bottle, and the gas for your car, what other purposes do I serve? Well, there are several fields where organic chemistry is utilized, so let's take a moment to quickly look at some, starting with biotechnology. This is a branch of organic chemistry that modifies living organisms for other purposes. For example, about 80% of the papayas grown in Hawaii have been genetically modified in order to be resistant to a certain virus. Then there's the pharmaceutical branch, whose goal is to develop medications to treat and cure diseases. So far, most of what we've talked about is organic chemistry and living organisms, right? I guess I briefly mentioned gasoline and plastic, but that's about all. What if I were to tell you organic chemistry is pretty important to many fields not involving organisms that are currently living? For example, although crude oil is made from tiny organisms that once were living, they certainly aren't now, which leads us to the petroleum field, where people try to find, extract, and refine petroleum. Or the chemical field, where raw materials like petroleum, crude oil, and metals are made into 70,000 products, including rubbers, plastics, and textiles. See, I really am everywhere. You should know by now that Callie Carbon isn't just a pretty face. I am so important I get my own branch of chemistry, called organic chemistry. Let's take a moment to review some important terms and ideas. Organic chemistry studies carbon-containing molecules and the compounds they form. Organic chemists look at the reactions, the structure and composition, the properties, and how organic molecules can be prepared. Carbon is special because it can attach to 4 other atoms, and it can do so in many different ways, from rings to chains to double or even triple bonds. This results in many different types of organic molecules. These organic molecules make up the building blocks for living things, so you are a carbon-based life form. There are many fields that require a firm understanding of organic chemistry, from pharmaceuticals to finding and extracting petroleum. So yeah, you shouldn't forget me. I mean, I'm all around you, and without me, you wouldn't exist.